Mn by 1, F transpose is 1 by Mn. So this is an Mn by Mn matrix, Ff transpose. Whereas F transpose F is a single quantity, 1 by 1. And take the trace of the matrix, that is the sum of all the diagonal elements, then that is the energy of the image. So instead of writing the energy as sum of m going 0 to m minus 1, sum n going 0 to 1, 0 to n minus 1, f square mn, you just write it as f dot f or f transpose f. Even the dot notation is not commonly used in matrix operations. So f transpose f or f prime, sometimes instead of t, the prime is used. Or outer product. Sometimes you may need the outer product to get the cross terms. If the image elements or pixels are considered to be random variables, which we said we do earlier, if the image is corrupted with noise, noise is random, so the combination of noise with image is also random, then you want to take the mean is expectation of f. So it is just an algebraic variable that you have put in these expressions, which is an mn by 1 matrix or vector, expectation of the entire matrix, not the average value, but expectation of this means you have a number of images and you are taking the average of the images, an ensemble average, or statistical expectation of the entire image. Covariance, expectation of f minus f bar transpose, which turns out the expectation of ff transpose, f bar transpose. And this is an mn by mn matrix. Now, suppose you have a 1000 by 1000 image, which is fairly common, or your camera gives you 6K by, my camera gives me 6K by 4K. Yours may give you, I don't know, a billion by billion pixels. But if you have a 1000 by 1000 image, which is not very big nowadays, this will be a million by million, this matrix. Well, that's going to be very huge, and you may not have the capacity in ordinary computers when you have even larger images, medical images. So these are mathematical representations to facilitate the derivation and representation of operations. You may not do it this way in computation, or you may have to take some special, develop special algorithms to compute them as needed. You may not have the storage capacity to handle this. So you have an mn by mn matrix. Along the diagonal, we have the variances of each pixel. And the other sigma 1, 2, sigma 2, 1, sigma 1p, sigma p1, sigma p2, they are the cross correlation or cross variance between various elements. So this way we get the cross terms. Sigma pq is expectation of fp, okay, fp minus fp bar, fq minus f bar q. That is two different pixels. So you get the cross relationships here. So sigma pq is the covariance between the pth and qth elements of the image vectors. Sigma is symmetric. Sigma pq is sigma qp. The diagonal terms are the variances of the elements of the image vector of each one. But this is across a population. You need a population of images. You cannot compute this for one image. That's why we have the expectation operation. In practice, the expectation operation is replaced with a summation over a database of images. The autocorrelation matrix is expectation of ff transpose. There is no subtraction of the mean. That's all. And this is also an mn by mn matrix. And if you normalize covariance, sigma rho pq is sigma pq divided by sigma pp and sigma qq, then the diagonal elements are 1. And then you have the covariances on the other sides. And it is symmetric again. The absolute scale of variation, the sigma values along the main diagonal are in another diagonal matrix D. Then this sigma is d rho d. Sigma is this one, the covariance matrix, where we had the variances along the diagonal. When you normalize, the diagonal is 1, but you need this to keep that factor of the variance. Then sigma is d rho d. If the mean is 0, then the autocorrelation and covariance are the same, but in images, it is not common to encounter 0 mean. So using this notation, we can redefine some of the statistical properties. Two images are uncorrelated if expectation of f g transpose is expectation f, expectation g transpose. That is, the expectation can be separated. Expectation is like integration. The two can be separated out if they are uncorrelated. Then the cross covariance matrix sigma fg is a diagonal matrix, and the cross correlation phi fg is an identity matrix. They are orthogonal if the projection of one onto the other is 0. When you project one vector onto another, if it is 0, then they are orthogonal. They are statistically independent if the probability density function joint PFG is PF times PG. Then F and G are also uncorrelated. So these are some basic statistical properties expressed now using this matrix notation, which of course you would do with ordinary variables. Expectation of xy is expectation of x times expectation of y, where x and y are just scalar variables. But now they are matrices representing entire images. Okay? Is that clear? Okay, now how do we apply transforms to this representation? Transforms such as the Fourier transform. So let's start with some basic 1D transform of some kind. We don't specify what it is. Let's start with a single dimensional, one-dimensional signal, f of t, and you can use continuous notation first, and then we will switch to discrete. So f of t is ak some phi kt, where the functions phi k are the basis functions, and for that they have to be mutually orthogonal. So mutually orthogonal means the projection of one onto the conjugate of another, phi kt, phi l star t dt, integrated, is some constant. If that constant is 1, then they are called orthonormal. The Fourier transform has sinusoid functions which are orthonormal. So the signal is expressed in terms of these functions with some weights ak. So ak is obtained by taking the projection of the given signal onto the conjugate of each of these basis functions, phi star k. So this is like the transform to get the coefficient values given the signal and the basis functions. So ak is the projection of ft onto phi kt. So this set of functions phi kt is said to be complete or closed if there exists no square integrable function ft for which the projection of that signal onto that function is 0. In that case, that function should also be a member. So for the Fourier transform, all sinusoids, sine, cosine, and for plus and minus frequency to infinity, plus and minus infinity, they're all included in the basis function. In the DFT, it is limited, as we will see. So ft is orthogonal to all of the members of the set of this phi kt functions, and then it is called an orthogonal or orthonormal basis set, or just basis for the transform. The Fourier series representation of periodic signals uses an infinite set of sines and cosines at integral multiples or harmonics of the fundamental frequency of the given signal. So that is an example. We will see details soon. And these functions, phi kt, all these basis function members, and the given function ft must be square integrable. That is, they must have finite energy. There are some other conditions, but right now we will only use this one condition. So suppose now you have a 1D signal as an n by 1 vector or a column matrix. We can represent transforms using n by n matrices. L. Capital F is the transform domain. Small f is the input time domain or space, whatever that domain is. L is the transform. So now you can write f equal to LF. Capital F is equal to LF. So that's a very simple representation of the transformation, but how do we write L? We need to see that now. And then the inverse transform is the original small f is L star transpose, the conjugate transpose, times the transformed space quantity. Now L times L star T must be equal to I, the identity matrix.
Sir, what about the other? Is it unitary? Is it unitary man?
Which one?
L.
The identity matrix. No. L is the transform. L is like the DFT, as you will see.
The matrix corresponding to transform. The matrix corresponding to transform.
Yes. The elements of the matrix will have values of the basis function. So if you open it up, then Fk is summation L n going 0 to n minus 1 Lkn Fn. Fn is the input signal. And Fn is the sum on k going 0 to n minus 1 L star Nk Fk. We are writing it as just L. It could be any transform, DFT, Walsh transform, Hadamard transform, and so on. So this is the forward transform, inverse transform. So now let's look at the DFT, which you're all familiar with. So for DFT, L is defined as Lkn equal to exponential minus j2 pi over n, capital N, the number of samples times Kn. N is the time index, K is the frequency index. That's the DFT kernel function, basis function. Now in the FFT algorithms, typically this is written as W subscript n. How many samples do you have around the unit circle, as you will see, or in the signal and the DFT? Exponential minus j2 pi over n, the frequency index is taken out, or both indices are taken out. It depends only on the number of samples in total in the signal and DFT. Then Lkn, the knth element in that matrix, is W sub n to the power of Kn. So Fk, the DFT, is Fn times this quantity. This is the standard DFT, right? K going 0 to n minus 1, and n also goes 0 to n minus 1, right? So if you want to write it out as a matrix, that is the DFT. This is the input signal. This is the DFT matrix, L. So what are these W's? Exponential of minus j2 pi over n times that power, 0 to n minus 1 times n minus 1. K and n going 0 to n minus 1. So the row index and the column index will go 0 to n minus 1. Now, there are some advantages with the sinusoids. There is some repetition of the same values. That is how you get the advantage in FFT, by making use of periodicity and the relationship between the sine and cosine functions. So because of periodicity, Wn to the power of m times n minus 1 is the same as W to the power of minus m, or W to the power of n minus m for any integer m. So multiplying by an integer doesn't change. And W to the power of n is equal to 1. So for a given n, there are only n distinct functions. It's an n by n matrix, n square values, but there are only n values that are unique and they are repeated. So W to the power of k sub n, those are the unique values. Others are just repetitions. There's a nice figure that was given by Hall. where you see the unit circle, that is supposed to be a circle. Is it possible to adjust the aspect ratio? Because later on, when we do shape analysis, we need to look at the shape properly. Right now, it's okay. So this is a circle. It looks like an ellipse because of the projection. So the DFTs is obtained by sampling around the unit circle in the Z domain, right? You know the Z transform. And when you go around the unit circle, magnitude Z equal to 1, then Z translates to the exponential function. And this is W using n equal to 8, W sub 8. The powers 0, 1, 2, 3, 4, 5, 6, 7, and then 0 again, the same thing happens. There are only 8 values, but the matrix is 8 by 8, 64. The same values repeat. So the transform DFT going 0 to n minus 1, the input signal going 0 to n minus 1, you only have these values. Wn to the power of 0, 1, 2, 3, so on, n minus 1, and the same values repeat. So that is the DFT matrix. Now we don't have 64 or n by n values, we only have n values. Specifically for n equal to 8, 0 to 7, this is the DFT. 0 to 7, that's the input. And here you have the W function. The sub 8 has been removed. And it's only to the power of 0, 1 through 7. So that's the DFT matrix. Now you can write the one-dimensional, this is one-dimensional, DFT of a 1D signal using a matrix. And there are some papers on FFT algorithms using matrix notation to show that FFT can be achieved by some properties as we are seeing now. Is that clear? Okay. So now let's go to 2D. FKL, the transform is given by FMN, the input, multiplied with this kernel function or basis function, which now has 4 dimensions. In the 2D case, the kernel function had 2 indices. The input has 1 index, but the transform has 2 indices, k and n, n for time, k for frequency. Now, the input has 2 indices, m and n, for x and y coordinates. The output has kl for 2 frequencies, horizontal and vertical frequencies. So the kernel function has 4 indices, m, n, k, l. So if you have a 3-dimensional image, then the input image has 3 dimensions. There will be 3 frequencies. The kernel function will have 6 dimensions. So FKL is written as FMN times phi mn KL. Why is only that turning off? Everything else is okay. Is it getting heated or? Okay. And Fmn, the inverse transform, is FKL times some other function psi mn KL. So what are these? The forward transform kernel and the inverse transform kernel of some transform. We assume that they are separable, which means phi mn KL can be written as phi 1 mk, one input variable, one output variable. That is one space variable m, one frequency variable k. Phi 2, another space domain n, another frequency variable l. And symmetric if phi 1, phi 2 are the same, like in the DFT exponential. Then you can compute the 2D transform in 2 steps, one along the rows and the other along the columns. You take the result of the first transform. So first one is F1 ml is Fmn times phi nl on n. This is a function of n and l. So this is the output of the first transformation, which has one input index m, one output index l. Now take that and apply the second function phi mk, you get skl, the final transform output. In the case of the 2D Fourier transform, phi mnkl is exponential minus j2 pi over n mk plus nl. We assume n by n square image, and that is separable like this. So this is like a 1D DFT function. Just the index variables are different, right? Then the 2D DFT may be expressed as capital F, the transform is WFW. Lowercase f is the input image, capital F is the transform, Fourier transform, spectrum. So F is the input n by n matrix, W is a symmetric n by n matrix. We will see another representation where it is different. Okay, please note here, these are all n by n matrices. We haven't done the column ordering in this case, or row ordering. And Wn to the power of km is this exponential function which we have seen already. There is periodicity of Wn, so this matrix W has only n distinct values, as we have seen. Now there is pre-multiplication and post-multiplication for first column or row transformation, then transformation on the other dimension. Row or column, whichever one you want to do first. So WFW. But these are all n by n matrices. At the beginning I said we will convert the image to n squared by 1. But right now in this formulation, the image is still kept as an n by n matrix. And the transform is also n by n. Whereas for the 1D case, we saw for an n by 1 signal, the transform matrix was n square by n square. Oh, sorry, n by n. So the DFT matrix is symmetric, with its rows and columns being mutually orthogonal. The sinusoidal functions are mutually orthogonal. So WMK times WML star is conjugate, is equal to n. So that's why you have a 1 over n. If you put the 1 over n, then they become orthonormal. So then W inverse is 1 over n W star. You take that n and put it there. Then the inverse transform is 1 over n squared W star F W star. So the forward and inverse transforms are written using the same matrix W but conjugated. And they look similar, WFW. There is this factor 1 over n squared. In most books you will see 1 over n for the forward, 1 over n for the inverse, just for symmetry. But in most 1D cases, you put the 1 over n only on the inverse transform. But here we have 1 over n squared. So there are a number of transforms that may be represented in this format. F, the transform is AF. Small f is the input, capital F is the output of the transform. A is some matrix. Depending upon the transform, the matrix will be different. So the computational requirements may be reduced by taking advantage of the properties of the basis functions. So the DFT matrix in particular may be factored into a product of 2 log n, natural log n, of sparse and diagonal matrices, and that reduces the computation because sparse matrices have many non-zero elements and a diagonal matrix has only values along the diagonal, the others are 0. So by reducing this matrix that may have various real values into a series of matrices that are sparse and diagonal, you can reduce the number of computations, and that forms the basis of the FFT algorithm viewed in a different way. The original Cooley and Tukey algorithm was not developed this way, but there are other papers showing matrix derivation of the FFT algorithm. To give you another example, the Walsh-Hadamard transform is commonly used in image processing. It could be used in signal processing also, but it's not so common. Now here, the set of 1D Waltz functions is defined using this iterative relationship, phi sub n, the nth function of x is some variable, is phi 2x of n over 2. This is the order of the function. And phi n over 2x minus 1, depending on whether we are in the first half or the second half, and minus if n is even. So this is the integral part of n over 2. I'll show a picture which makes it more clear. Phi 0x is defined as 1. Phi 1x is plus and minus 1 for half the interval. The nth function is generated by compression of the function phi n over 2 into its first half and plus or minus phi n over 2 into the second half, like this. N equal to 0, all the values are equal to 1. So these are the first 8 Walsh functions sampled with 100 samples. There are 100 values here over the interval 0 to 1. So this is half of that index, time or space or whatever that is. So how do you get the first one? N equal to 1. You take this, compress, and you put it in the first half. And take that and compress and put in the second half. This is odd, so you reverse this, plus and minus 1. And for 2, you take this, 2 over 1, 2 over 2 is 1, so you take that, compress in the first half, and take that and compress and the second half, reversed, and so on. So for n going 0, 1 through 7, you get this. They're not sinusoids, they are rectangle functions. They're not squares. Some of them are not square. Okay? So Walsh functions are ordered by the number of zero crossings in that interval called sequency instead of frequency. It's not a sinusoid, so you don't call it sequency. No zero crossing. 0. 1 zero crossing. 2, 3. 1, 2, 3, 4. That's 5. 1, 2, 3, 4. This ordering changes depends upon the definition you use. So this has 5 and this has 4 zero crossings. So the sequency numbering and the way you generate using this rule, the order will be different. I'll show another definition. If the Walsh functions with the number of zero crossings less than 2 to the n minus 1 are sampled with n equal to 2 to the power of n uniformly spaced points, we get a square matrix representation that is orthogonal. I'll show you that. Rows are ordered with increasing number of zero crossings. The ordering of the Walsh functions varies with the formulation. That's what I wanted to say. I started counting, but 4 and 5 are switched with that formulation. The matrix is this, plus and minus 1. No zero crossing. Here 1 zero crossing, and so on. There. So because this has just plus and minus 1, you only have addition and subtraction. So computation is simpler. Previously, in the 60s and 70s, computers were not as fast as what you have now. And the Fourier transform used to take substantial amount of time. So there was interest in other types of transforms where the computation could be reduced, such as this, where it's only addition and subtraction, or the DCT, discrete cosine transform, for image processing. For signals, computation was not a big issue. When we started our work on digital image processing, we were working with little images, 64 by 64, 100 by 100, and so on. So in my book, I still have some examples that are fairly small images. But the mammograms that we have processed in our research work are 4,000 by 4,000 pixels for one image. 3D data sets of computed tomography, that depends on the resolution used. There could be 50, 60 to 100 slices in the chest and abdomen. And each one could be 512 square, 1,000 square, whatever. Depends on the radiation dose used and the resolution used. So then, the Walsh transform of a 1D signal is f equal to AF. like we saw for the FFT case. Now this is the matrix representation. There is another formulation, I don't want to read this, using the bits, the p bit in the p-bit binary representation of M. You read that later on. To read that, it makes no sense to read that. -1 to the power of something where the bits are used. But I think that is clear, and this is clear. This is, I think, for computer scientists. The major advantage of the Walsh transform, the kernel has only plus and -1 values. Addition, subtraction. Identical operations in forward and inverse transformation. So except for ordering of the rows, the discrete Walsh matrices are equivalent to the Hadamard matrices of rank 2 to the power of n. A2 is 1, 1, 1, -1, and A2n is an, 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 minus an. So you repeat the same thing. Take this, repeat, repeat, and minus here, and you get a matrix of double that size. Then if you define A is 1 over root n of an, the Walsh-Hadamard transform of a 2D function may be expressed as f equal to AFA, both ways, which were forward and inverse. Where all matrices are n by n. Okay? So these are the first 64 Walsh-Hadamard 2D basis functions. Black is -1, white is +1. So just one change here. And here you get a chessboard pattern. Increasing horizontal frequency, increasing vertical frequency in some manner. Compare this with the sinusoids I showed earlier. I wanted to create these patterns. A few books have this, not many books have these pictures. I spent some time creating these in MATLAB. Hopefully they illustrate the nature of these functions. What do they look like? Any questions about this? You may need to work through this later on at your convenience. I'm sorry?
Types of transformation was later on, but before that, for a single image, you needed transformation many times. Why is it necessary to do the transformation many times?
Why is it necessary to do the transformation?
Many times.
Many times.
Yeah, before the topic that you covered, types of transformation was not before that, even transformation 3 times a day. Why should we do 3 transformations?
I'm still not understanding the question. Why are we studying transformation again? No.
Why are we applying transform to the image more than once?
Where are we applying it more than once?
We did it. We applied at least 3 times.
I expressed the transformation in a different way. We use the conventional array notation of transformation. We are not applying it again. This is simply a different formulation, right? So here, this f, small f, is still the original image. This is simply a different formulation of the transformations we talked about earlier. I showed the Fourier transform. I showed the Fourier transform of pictures. I didn't say how we computed the Fourier transform, right? I just assumed everybody knew that. But now we are looking at how the Fourier transform, not how it is computed, but how it is formulated. We are looking at the details. Is that what you wanted to know? Yeah. So we are not repeatedly applying. Sometimes we do have application of the transform multiple times in a whole algorithm where you go one transform to another and back and forward. Like in homomorphic filtering, I'll show you later on. But here we are simply looking at formulations in the function format fxy or f capital F uv, or in the discrete notation fmn fkl, or in the matrix notation as f equal to afa, and so on. At the beginning I showed examples. Now we are backtracking a bit and looking at the representation. So I'm mixing the two so that we don't do all of this mathematical material at the beginning and leave all the examples to the end. So I'm mixing that. Is that what you wanted to? Okay. Any other question? We are doing this, as I mentioned at the beginning today. This formulation is required, or I shouldn't say required. This formulation facilitates the derivation of optimal filters. At the beginning, we did not look into optimization of filters. We just said this is the transform, and we applied some filters using space domain operations and frequency domain operations. We didn't say how we got to the frequency domain. And we didn't say they are optimal. We said try this, try this, try that. If you like it, fine. If not, try something else. But next we will see, after this, optimal filters. In order to optimize a filter operation using sub-optimization procedure, derivatives are required, expectation operations are required. Then this formulation facilitates that kind of derivation. That's why I'm bringing this here. If we don't see this, it will be hard to show the Wiener filter, for example. Okay? Now convolution. How do you represent convolution using matrix representation? Earlier we saw convolution, that one signal is kept the way it is, the other signal is reversed. If it is image, you have to reverse this way and that way, and then multiply and shift and get the output for all shift values. But how do you do it in this matrix notation? So I call it matrix vector multiplication, but it is matrix multiplication. A vector is also a matrix. So let's start with a 1D representation. Gn is f alpha hn minus alpha. F is the input, h is the impulse response, and alpha is some temporary variable, and minus alpha represents reversal of h, and n is the shift, and the output is given for that location. Assuming causality, alpha starts from 0 and goes to n only. If you want, for the sake of generality, you could write minus infinity to infinity, but causality is usually included when you go 0 to n. If the input is given over n samples, we could represent the output over that range 0 to n as g equal to hf. So this is the matrix representation for 1D. F is an array like that, 0 to n samples. G is the output. This matrix H now is computed using the values of the impulse response. Matrix multiplication, you take this and put on top of this row and multiply F0 times H0, and the rest are all 0. So G0 is H0, F0. So the matrix has only the first element of the impulse response. For the second one, you have the first H0 and the H1, causality. And then 0, 1, 2, and so on. Then at the end, you have all the values. So what do you get? Gn is F0 times Hn, F1 times Hn minus 1, and so on. So write that and check with the equation, and that is correct. So H now, this matrix, it is not diagonal, but there is a whole bunch of zeros there. It is said to be Toeplitz-like, but I'll show Toeplitz matrix later on, which gives some computational advantages because of these zeros. A Toeplitz is a square matrix where the elements are equal along every diagonal, but that's not the case here. This is equal, that is equal, and so on, but the other side doesn't appear that way. There will be zeros in the lower left portion here if Hn has fewer samples than Fn and Gn, and H is then said to be banded, zeros there and zeros here. the impulse response will not be long. Of course, there are filters with infinite impulse response, IIR filters. But if your filter is an FIR, finite impulse response filter with only 3, 4, 5 samples, but the input is long and the output is also long, then this matrix will only have maybe H0, H1, H2, and everything else is 0. You still have to write an n by n matrix for multiplication, right? So G equal to HF is convolution. The projector is getting tired of my equations. If the impulse response has a finite duration of m plus 1 samples, FIR filter, then you may center the impulse response at the point where you're getting the output, both sides. Then you write the index as alpha n minus m over 2 and plus m over 2, f alpha h n minus. It's the same convolution, but now the index doesn't run 0 to n, but it's a moving window operation. The signal is long, you're computing the output here, and the window is centered there. The impulse response is centered there. You can also change variables and write that way. I won't read that. So here also you can write it as GF, but the matrix has to be written this way. I'm sorry, it's a little difficult to read that, but so you have hm over 2 to h minus m over 2, the impulse response. Now having positive and negative indices, h0 is in the middle, and that is shifted for every row. So each row is a right shift of the previous row. The input is also written going from minus m over 2 to n plus m over 2. If it is causal, then the negative index values will be 0. The output is obtained for 0 to n for causality. But input may not exist for negative values. This is simply notational convenience. Although these are causal, you can impose causality on this. So H is now said to be banded and toplets-like. Each row of H except the first is a right shifted version of the preceding row. And M is less than N. FIR filter has a small short impulse response. The input could be much longer, and the output. Okay? So this is banded in the sense there are zeros there, there are zeros there. These are not diagonals, but the same values occur in bands. And each row is a right shift. The same values occur here, but with a shift to the end here. There is another type of convolution known as periodic or circular convolution, which is what you get when you use DFTs. When you take the DFT and multiply and come back to the time or space domain to achieve convolution, then what you get is not linear convolution, but circular or periodic convolution. But you can get the equivalent result by zero padding. Now in this case, periodic or circular convolution, all the signals are assumed to be periodic. As I mentioned earlier, when you sample a signal, sampling implies periodicity of the spectrum. The frequency domain function becomes periodic. When you compute the DFT, you're sampling the Fourier transform. So sampling the Fourier transform implies that the time domain function is also periodic. So the DFT pair, forward and inverse, the signals are periodic going around the unit circle in the Z domain. So if you go round and round, you get the same thing. You're sampling around the unit circle. So all signals are periodic. But if you have a non-periodic signal, you simply say, well, it is one period of that periodic signal. I don't care about the other periods. I'll just take one period, let the others be there, theoretically. Theoretically, yes, but sometimes there are implications of aliasing errors if you don't take care. So it is not simply some theoretical stuff, but there are implications of aliasing unless you take care with adequate number of samples. So if they're all periodic, shifting is periodic. Linear shifting, you shift each sample at a time and it keeps going. Periodic shifting, if this is the period, if you shift, the sample that goes out will come back here, shift again, another sample comes here. So you're always having n samples. And what goes this side will come back the other end. Some books say it's like having samples written on a drum. If you rotate the drum, the same samples keep appearing. So GP and P is periodic. FP alpha, HP, n minus alpha mod n. So that index has to be periodic, only between 0 and n minus 1. So the shift is given there, and alpha going 0 to n minus 1 over one period. Excuse me. Did we say we go 9:30 to 10:30 or 11? 10:30. Okay. Okay. Oh, 2 more minutes. We started 5 minutes late. The result of periodic convolution of two periodic signals of n samples each is also a periodic signal, whereas the result of linear convolution would have two n minus 1 samples. Linear convolution gives you a longer output because you keep shifting until there is no overlap. And the shift has no limit, whereas here the shift has a limit because of periodicity. So that's an important property to remember, that the linear convolution of two signals with n1 and n2 samples will have n1 plus n2 minus 1, or in this case 2n minus 1 samples. Periodic, n1, n2 cannot be different. The two signals must have the same period, real or assumed. And then the output will also have the same period. But linear will have more. So how do you get that? Periodic convolution may be used to achieve the same result as linear convolution by padding the signals with zeros, so that you increase the duration to at least 2n minus 1. If you want to have more, go ahead with more, but it will be a waste. There won't be any more samples. So just pad with zeros. So you must use 2n minus 1 samples. So implementing convolution as the inverse DFT of the product of the DFTs of the two signals implies periodic convolution. Otherwise, if you don't take care of this, you get some wrong result. Zero padding will be necessary or required if linear convolution is desired. In the case of a causal linear shift invariant system, what you want is linear convolution. Periodic convolution may also be expressed as G equal to HF. F has 0 to n minus 1 samples, G has the same. Now the impulse response is written with H0, and what was shifted out will come back here, H1, 2, so on, Hn minus 1. You shift, H0 goes there, H1 that was here will come here, and so on. At the end you get 0, 1, n minus 1 in reverse order because of the reversal in the convolution integral or sum. So if you want, you can take this, F0, multiply with this, F0 Hn minus 1, F1 Hn minus 2, and so on, Fn minus 1 H0 is Gn minus 1. Take the convolution in sum or integral and work it out. That works. Now each row of H is the right circular shift of the previous row, including the end. Shift this, H0 comes here, which is that. So bottom to top also right shift works. And this is called a circulant matrix. It is a square matrix. It is a circulant matrix because each one is shifted in a circular manner and also bottom to top. So that is a nice representation of circular convolution or periodic convolution, the same G equal to HF. The variation is only in this. How do you formulate this matrix H? And in 2D we will see how to do that. So we'll stop here. We'll take a break now. Just a moment. Yeah? You have to speak up. There's fan and everything.
In practical implementation, while performing circular computation using DEPT, how do we make sure that the output matches the exact result of the linear column?
I'll give you some numerical examples soon. All you have to do is pad with zeros. And then you extract the required portion. In the output, you will have, if you pad with more zeros, the non-zero values will give you the output and the other values could be ignored. They'll be zeros. I'll show you some numerical examples. It is possible to achieve linear convolution using this procedure. And I'll show you the matrices. Okay?
There's one more doubt from the previous one. Can the cost function be used in ultrasound imaging to less down the spicules and also maintain the edges?
The Walsh transform is just a transform. What you do with the transformed function is up to you. You can achieve filtering. I have not used Walsh functions for filtering. Walsh-Hadamard functions have been used more for data compression and so on. Filtering is typically done using the Fourier transform because you have a better understanding of the frequency. Here you have sequency and it's a little harder to correlate sequency with the nature of noise. So I have not seen good examples of filtering using the Walsh-Hadamard transform. But I have read papers where it's used for data compression. What you do with the transform is up to you, whether ultrasound or any other image. How you filter depends on how you interpret those components. And since I have not used them, I cannot tell you how to interpret the frequency components of the Walsh-Hadamard transform. It's a theoretical nicety. I have not seen many papers where it's been used in practical applications except for data compression.
So learning folks are trying to use it, and the learning folks are trying to use it. That's it.
Okay. Any other question or comment? Okay, let's take a break. Thank you.
Okay, we have half an hour break.
Half an hour is 25 minutes now.
To come forward because he has just fair ball.
For convolution in one dimension for 1D signals, fk, hn minus k going 0 to n minus 1. You write the function fn, but now you switch the variables to k, and hn becomes hn minus k. So what you have to observe here is k is the index of integration or summation, going 0 to n, 0 for causality starting from the origin, not before, and n again for causality because you can only look up to fn to get the output fgn. You cannot go ahead. So causality implies both these limits, 0 to n. And hn minus k, h is now having minus k reversal with respect to the variable of integration or summation. N is the shift at which the output is computed. Okay? So h needs to be reversed with respect to the index of summation k and shifted by n where the output is to be computed. The index n may be run over a certain range of interest or over all of time for which gn exists. After that, when it's all 0, you stop. So gn is computed for n going 0 to whenever. But we know that when you have two signals of samples n1 and n2, the output has n1 plus n2 minus 1. Samples for linear convolution. So for each n, the reversed and shifted version of h is multiplied with the signal f on a point-by-point basis, like a dot product. And multiplication and summation operation together are comparable to the dot product performed over the non-zero overlapping parts of the two signals. So let's look at this simple example. Fn is 4, 1, 3, 1. For n going 0, 1, 2, 3, hn is of a different duration, 3, 2, 1. Usually impulse response is decay. for n going 0, 1, 2. So the two signals are of different length. The result G has more samples. We'll have 4 plus 3 minus 1. 6 samples that are non-zero. There could be zeros in between. So the result of linear convolution will have n1 plus n2 minus 1 samples. Okay. So these are the indices. N for the input, Fn, Hn. This is what we defined as an example. K is for the convolution index. K going 0, 1, 2 up to whenever you want. Let's go up to 7. Fk is same as Fn, 4, 1, 3, 1, and a bunch of zeros at the end. So reversal, H 0 minus K, which is H minus K, is from K going 0, 3, 2, 1, 0, going backward. But we don't work on the negative indices. It doesn't matter. We will just write it here. So this is a reversal of 3210 written as 3210, starting from K equal to 0 going backwards. 1 minus K you shift, and 2 minus K shift again, 3 minus K shift again, 4 minus K shift again. And you take a product point by point or sample by sample product of this with Fk. Fk is that. In this case, only one sample will overlap. 4 times 3, 12. Here, 3 times 1 plus 4 times 2, 11. So keep shifting and multiplying those samples that overlap. And finally here, 0, 1, 2, 0. What do we have there? Yeah. 6 minus K. Yeah, the Gn will be 12, 11, 15, 10, 5, 1, 0, 0. So for the last two samples, 6. The 6, n equal to 6. There is no overlap. 0 with 1 and everything else is 0. So if you want, I can compute for 7 minus K, 8 minus K, they will all be 0. So these are 0. So you only have these samples, 3 and 3, 6 samples. 4 plus 3 minus 1, and 1 plus n2 minus 1 samples. So this is linear convolution. Whether you call it K or n, it doesn't matter. It's an index. So that's the output of linear convolution. Now you want to do it in matrix notation. You write 4, 1, 3, 1 and put 2 zeros because we want to allow 6 samples in the output. This is linear convolution using matrix notation. So convolution in 2D. This is the expression we have seen earlier. The range of summation we will allow for the whole range just for the sake of convenience. You don't normally do that. Your convolution kernel is much smaller than the image. The image could be 1,000 by 1,000 pixels. Your convolution kernel may be 5 by 5 pixels. So your integration or summation is done only over that much. The rest is 0 for the impulse response. The image has non-zero values, but it doesn't matter. For the sake of representation, we will just let it run 0 to n minus 1. If the point spread function is much smaller, you can also let the index run minus m to m. The kernel is of size 2m plus 1 by 2m plus 1. Typically, the kernel is of an odd size, 3 by 3, 5 by 5, and so on. So this representation is convenient then. And then you center the convolution mask on the pixel being processed. You use all neighbors above, below, left, and right within that matrix of the convolution kernel. So then you are making this summation go only plus minus m, the shift, which is applied to h. This is the image, f alpha beta. Okay? The image is of some size n by n. The output is also of some size n by n, but the matrix of the convolution function, the filter, is 2m plus 1 by 2m plus 1, which is much smaller than the size of the image. So the point spread function is reversed, flipped, or reflected in both dimensions. For the signal, we just reversed in time. Now we have to reverse this way and that way. Both of its axes placed on top of the input image at the coordinate where the output is to be computed. A point-by-point multiplication of the values will be performed and added. It needs to be performed for every spatial location for which the output exists or is required by dragging or shifting the impulse response over the image. In most cases, the point spread function of imaging systems will have some symmetry or even isotropy. So symmetry means if you flip this way or that way, that way, it doesn't matter. So that reversal is not necessary. So then you just use it as a masking operation. Convolution is also a masking operation, but you need to reverse the impulse response matrix before you do the masking. But if the impulse response has symmetry about both the x and y axes, then reversal is not required. So here we have an example, some numbers. I just put some numbers there. And this is the point spread function. You reverse it. So 7, 8, 9 comes this way. 1, 2, 3 goes that way. And then you flip vertically. This 9, 6, 3 goes there, and 7, 4, 1 comes here. So this is the reversed or reflected point spread function. Now that's the image, 1, 2, 1 something. And I have put this reversed impulse response at this position. And you multiply these values 9, 6, 3, 8, 5, 2, 7, 4, 1 with these pixel values 1, 1, 2, 2, 2, 1, 2, 3, 4. You get 79, which goes at this location in the output. And do that all over. You won't believe it, I have done this by hand, and then I put it in MATLAB and checked. And that is correct. If you want, you can also do that. Okay? That's 2D convolution. Now, there is another representation of the DFT. We saw earlier that we could write the DFT as matrix multiplication. But now we will see a slightly different representation. We will start with what is called a circle-length matrix and see how it is converted to a diagonal matrix by the application of the Fourier transform. A circle-length matrix has values like this, the same values 0 to n minus 1, right shifted to the end and also from the bottom to the top. So it's an n by n matrix, but there are only n values that are unique. So that is a circle-length matrix. So again, let's represent W as exponential j 2 pi over n. Wk capital N will be equal to 1. And Wkk equal to 0 to n minus 1 are the n distinct roots of unity that form the basis functions of the DFT. We saw the unit circle and those values of W earlier. Now consider this lambda k formed by multiplying the first row C0, C1, Cn minus 1 with this series of W values. W0 is 1, Wk, W2k, so on, Wn minus 1k. So then if you multiply lambda k with Wk again, one of these values, Cn minus 1, will have Wnk, which is 1, so that has no W associated with it. And C0 will have Wk and so on. And multiply again, then Cn minus 2 is liberated of the W factor and so on. So what is happening is a kind of a right shift as you go along. As you multiply by Wk, W2k, Wn minus 1k, these coefficients C get shifted out. So this can be represented as lambda k, Wk is C, Wk. C is that circle-length matrix. Wk is the series of these coefficients. We haven't written it there, these coefficients. Wk, it's actually here, that series of values. With this formulation, lambda k is an eigenvalue and Wk is an eigenvector of this circle-length matrix C. Now there are n values Wk, k going 0 to n minus 1 that are distinct, and there are n distinct eigenvectors Wk. And then you can write an n by n matrix W as this W0, W1, W so on. And That is related to the DFT, where this nkth element W is exponential j2 pi over n nk. This is the DFT kernel, 1D. Now this is an n by n matrix. Each one of them is a vector. So there is the property of orthogonality. So W inverse is 1 over n exponential minus j2 pi, that kernel function. W inverse or W inverse W is I, the identity matrix. And the columns of W are linearly independent, so they form this transformation. This eigenvalue relationship, you have a diagonal matrix now. W lambda is CW. So all of these are n by n matrices. Lambda is a diagonal matrix whose elements are equal to these eigenvalues. And you can also write it as C is W lambda W inverse. So this relationship is now interpreted as the circulant matrix we started with is equivalent to a diagonal matrix with the application of the DFT. DFT being applied here. Or this way. Or from the diagonal matrix, by the application of the forward and inverse transforms, you can recover the circulant matrix. So a diagonal matrix represents the circulant matrix. And the values along the diagonal are the eigenvalues of that matrix. So you're extracting a compact representation. So going back,
Similar to PCA type.
yes. Here we are using the transformation. With PCA, then you select the lambda coefficients that you want to keep and reject the low energy coefficients that you are not interested in, or those that do not contribute much to the representation. So you rank order the lambda case in order of decreasing values and throw away some at the end. Keep 90% or 95%, and you achieve data reduction. Here we're using it in a transformation. So going back to the convolution representation, we had H, the matrix that was formed using the impulse response, and we saw that it is circulant for periodic convolution. So DFT gives you periodic convolution. So we will keep it as periodic. And because it is circulant, H can be written as WD. We'll call it DH because the diagonal matrix from H. W inverse. DH is a diagonal matrix corresponding to the lambda values of H, the impulse response. So the elements of DH are given by multiplying the first row of matrix H with W and K, which is the DFT. It's a matrix, but the first row is just the DFT. HK is H0 and so on. WK, W2K, that's the Fourier transform. HK is the DFT of HM. So this series of values of H represents Hn minus n. So minus, which is equal to H minus n. So there is a reversal in convolution. That's why you get H minus n. So the series W will have the DFT kernel function. In 1D, having two variables, but you have post and we have the other dimension elsewhere. Okay, it is still blinking. So if you want the usual forward DFT, then switch the variable minus n to m, and then G, the output, is written as G equal to HF. That's what we wrote earlier for convolution. Now G is WD W inverse F. So convolution is now expressed in terms of multiplication of matrices formed using the impulse response and the input image G equal to HF. But H itself is expressed now as a circulant matrix and then further diagonalized using the DFT. W inverse F is the forward DFT of W, this one. And then multiplication by DH along the diagonal we have the Fourier transform coefficients related to the DF, related to H, the impulse response, which is the frequency response, H omega, HK, whatever you want to call it. So this is taking the Fourier transform of the input image, then multiplying by the Fourier transform of the impulse response. This is the inverse Fourier transform, back to the original domain. So the multiplication of the Fourier transform of the input signal with DH corresponds to point-by-point transform domain filtering. And this W does the inverse DFT. That scale factor 1 over n needs to be taken care of. So we have the convolution relationship we wrote like that, H star F, Hn star Fn for 1D, Gk, Hk, Fk, if you take the Fourier transform, multiplying the DFT coefficients, and G equal to Hf for convolution in matrix representation, and W dW inverse F, the same thing, with the DFT included now. So there are these representations, but this is different from what we saw in 367. Let me go back to 367. There, F equal to WFW. In that representation, we were using n by n matrices for everything, and these are images. So F is an n by n image, W is an n by n matrix. So this representation is slightly different from the one that we are seeing now. The one we are seeing now has a signal, a 1D signal. But of course you can convert a 2D matrix to a 1D matrix or array, as we have seen, and then the same thing applies. Okay? So there are these differences in this representation, or multiple representations if you want to call them so. Okay, now the next step. To do this in 2D, F represents the input image now to a 2D filter, and G is the corresponding filtered image. The 2D arrays have been converted to vectors or column matrices. So we'll assume all of these have been padded with zeros extended to m by n, and if you don't want m by n, make it n by n, and then these are mn by 1, let's say. The periodic convolution now is given in terms of GMN being this double summation F alpha beta H reversed, but now these indices are mod M and mod N within the period. So the result is also periodic in M by N. So G equal to HF. How do you get that again? So we have to take the matrix H now and see how we can formulate it so that G equal to HF works. So it's a question of formulation. You know what you want to achieve, and you define this accordingly. So you create this matrix H by taking the rows of the impulse response matrix and writing them in this manner: H0, the zeroth row, H1, H2, Hm minus 1, and make a circlet matrix of that arrangement. H0, H1, H2, so on, Hm minus 1, shift and shift and shift. The submatrices are given by as Hm, Hm0, Hm minus 1, and so on, and that is shifted in a circulant manner. So the matrix is of size mn by mn, or n square by n square. Each n by n submatrix here, Hm, is a circulant matrix. The submatrices are subscripted in a circulant manner here. And then H is known as a block circulant. It is not circulant by itself, but there are blocks that can be shifted and subsequent rows are formed that way. So it is a block circulant matrix, but this is circulant. So this is formed using the mth row and all the columns of of that impulse response. The same HM, different elements. Okay? So let's look at an example. I spent a lot of time to prepare this long ago. FMN, let's consider this some number, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just put some numbers, and I padded with zeros to make a 5 by 5 matrix. So the image has non-zero pixels only over a 3 by 3 region. And let us take the Laplacian. 1 minus 4, 1 all the way around. We saw the Laplacian earlier, right? So pad that with zeros to make it 5 by 5. So everything is 5 by 5. Now, the origin of this is in the middle. The origin of a matrix typically is taken to be that. So we have to rearrange this and put the origin there. So we get this matrix, minus 4, 1, 1, but what was above comes here, what was here goes there. Okay? So HMN needs to be rearranged this way. And if you do G equal to HF, you get this. You could work this out. There are negative values because the Laplacian is taking derivatives. Okay? And it's a 5 by 5 output. The images were 3 by 3, so 3 plus 3 minus 1, 5. There are a few zeros, but that doesn't matter. So what does H look like? Yeah. So this is the output G. This is the input image F. This is the block circulant matrix made using the Laplacian 1, 1, minus 4, 1 and minus 4, that's all. So how do you get this? You take the first row, all zeros, second row, 0, 0, 1, 0, 0, third row, 0, 1, minus 4, 1, 0, and so on, and make circulant matrices with each row. The first one is with that minus 4, sorry, not that, not with this one, with the shifted. The first one is minus 4, 1, 0, 0, 1. So take that, and that is the first row, and circulant matrix with that. The next is with the next row, 1, 0, 0, and 1, 1, 1 just shifted. Next has zeros, no problem. Last one had 1 there. And this is now block circulant, so shift this whole block there, and that comes here. Next shift this here, right shift, the whole block. So that is the block circulant matrix for 2D convolution. The input image is this, 0, 1, 2, 3, 0. Sorry, here, 0, 0, 0, 0, 1, 2, 3, 0, and 6, 5, 4, and 7, 8, 9, and 0. One row at a time, written as columns. And the output is that. Now we have to just rearrange this output, write that as the first row, second row, third row, fourth row, fifth row. So that is the output. You just have to recompose it. Okay? I'd never seen an example like this. I sat and worked this out by hand, and it took me hours to do that, and then check with MATLAB. Is that clear? You were asking a question how to do linear convolution with circular convolution. We saw with, sorry, you, there were two questions earlier. So we saw in 1D and 2D now. So how do you diagonalize this? That is possible. We won't go into the details of this. There is a paper I have referred to in the book. By the way, these notes don't have references. We don't show references in lectures. The references are all in the book. So all citations have been. I wrote the book using LaTeX, and these notes are in LaTeX, and I got a style file made to turn them into this format. So all the equations are retained from the original in the book, and all the figures are retained. I had to reformat the figures. But the book has all the numbers, equation numbers, figure numbers are the same. The references are in the book. If you're able to get the book from a library somewhere, I've given that old book to IISc Bangalore Library, PS College, Mandya Library, and a few other places. But don't buy that because it's outdated, 2005. The new book will come next year. If you can find it somewhere, there'll be some unauthorized digital copies floating around. You'll be able to find it. Don't tell CRC. We have told them, actually. They know, of course. But you have all the equations here. I have added 3 files, by the way. Initially, I missed sending chapters 7 and 8. I don't know if we will do chapter 7 and 8, or there is a combined reduced version called texture analysis. So there are 3 more files. Please go to that location and download those files. Depending on the time, we will see if I will do 7 and 8 in detail using these notes, or a compressed version in a different format. We'll take a look at that later on when we get there. So how do you diagonalize this? You consider the same Fourier transform. Now in WMKM is exponential j2 pi km and ln in the row and column matrices in the input and output domains. So define a W matrix that is Mn by Mn. For the 1D, we use n by n. Now you use Mn by Mn. Containing m square partitions of each of size n by n. One row of the impulse response at a time, as we saw just now. So the kmth portion of WKM is given by WKM, this function, times Wn. Wn, this is an n by n matrix, given by the DEPT coefficients. W inverse is also Mn by Mn, and it has partitions n by n, m square of them, and the partitions are given by this W inverse Km is W, this function inverse of that, Wn inverse. So similar to what we saw in 1D. I won't read all of that. So again, you can show, I won't go through that proof. There is a paper I have referred to in the book. H is WD W inverse, like in the 1D case. And we have these representations of 2D convolution, like 1D. GMN is HMN star FMN, and you can expand that with the double summation. In the Fourier transform, it is just multiplication of the coefficients of the Fourier transforms of H and F. G equal to HF, or G is WD W inverse F. The same thing. So if you've seen the formulation in 1D, it's the same thing here by converting the image into a column vector or column matrix. So considering an n by n image, the n square by n squared DFT matrix is different from the other n by n matrix we saw earlier. We saw 2 formulations. So it is different from the n by n DFT matrix where we wrote it as WFW. The image matrix F is of size n by n, whereas when you represent it as a vector, as a column matrix, it's n squared by 1. So there are multiple representations of 1D and 2D that you should watch out for in this discussion. So to end this part, why did we go through all of this? By the way, this representation has been discussed in detail by an old book on image processing by Hall, E.L. Hall, that I used as the textbook when I started teaching image processing in 1982. Gonzalez and Woods had a small book at that time. It was Gonzalez and Wintz. But this book Hall's book has more had at that time. He didn't come up with any new addition. All these details, mathematical details, and I found that interesting and retained that and expanded on that in my book also. Others have not gone through all of this information in as much detail. Some books have had it and later editions have dropped it. The tendency nowadays seems to drop all the mathematical niceties and just show pictures. In fact, there is a very big book called a handbook, Image Processing Handbook. I won't name the author. It only has pictures, beautiful pictures like an album. No equations. So one of my colleagues, when I gave these courses, was telling me, well, that book has all these pictures and describes image processing, but there are no equations. We need all the equations in order to understand how it is done. My students in Calgary have often asked me, why do I need to know this? It's all available in MATLAB. So I tell them, do you want to be a button pusher for MATLAB, or do you want to know and do what is behind the button and do something bigger and better so somebody else will push the button for you? So I don't want to be a button pusher. I want to know what is there behind the button and possibly design something bigger and better. Not making money. We didn't make money out of that. We add to the knowledge base. Maybe some will make money out of that. So, yes, it is important to know this. I hope I would say, some people say, did you enjoy it? It's not for enjoyment or entertainment. It is to learn something. I hope you find it beneficial, let's say. Or it may benefit you sometime later. So why? Now you can take derivatives. When you have F transpose G or G transpose F, take the derivative with respect to F, you get G. Like regular derivatives, because they are point-by-point multiplications, the derivatives will apply on a point-by-point. So the same vector is reconstructed as, note that this is partial derivative with respect to each element of F on each element of the output. And when you have F transpose WF, you get 2WF. Taking the derivative with respect to F, not W. W is the transform matrix. You don't take the derivative with respect to that. But the input variable F, the image or signal. So optimization of filters may be performed using matrix representation of images and image processing operations. Okay? Any questions? I've been giving my own comments in between. I should have waited for your questions and then said some of the things I said. Any questions about what we have done so far? Let's take a little break and have a discussion if you have any.
Eigenvalue setting can come down here. So here the eigenvector is kind of fixed for all the things. Circulant matrix can vary, like, because Fourier basis is fixed for.
Yes.
But in the PCA, the eigenvector will change.
No. The eigenvalues are related to the impulse response matrix. The eigenvalue DH that we wrote, that is related to the impulse response values, not the DFT.
So the Fourier coefficient will change.
The Fourier coefficients are in the other matrix W, WD, W lambda W. So the D matrix has the eigenvalues of the impulse response matrix, which will change depending upon your filter or operation in the kernel function, not the Fourier transform or Walsh-Hadamard, whatever. That's in the other W inverse or AA inverse, that matrix.
So the Fourier basis will convert any circulant matrix into a diagonal matrix.
Yes. But the circulant matrix was derived in this case from the impulse response.
From the impulse.
Yeah.
All the filters, all the transforms used in image processing, all are having these properties like separability or tonality.
No. The separability and so on, they apply to the transform, not the filter. The transform, the DFT, is separable. You may have other functions. If you use some other function, I can't think of something else. If you use some wavelet transform with some wavelet, you may not have the separability and symmetry. But here, because you're using complex exponential functions, sinusoids, then separability and symmetry comes in. Okay?
What are the major advantages of having separable orthogonal?
In terms of implementation and computation, a two-dimensional summation or integration is separated to a product of two integrals or summations on individual variables. But the transform, each transform, even in 1D, has two variables, one input, one output. J2 pi nk. N is for time, k is for frequency. Nk, ml. They were together as nk plus ml. When you separate, you get two separate integrals or summations. That means the 2D transform can be computed as a series of 1D transforms. So if you have an m-dimensional signal, then it is m 1D transforms with the DFT. If you design some other transform, you might not have these properties. The DFT, the Fourier transform, has these properties. That's why we're still using it. When was it? Fourier was in the 1800 something. You can check 1850 or something, 1840. So 160 years later, we are still using his transform. It's working. The others, some have come and gone. So when you have these properties, there are some advantages. An interpretation of the frequency content is easier, and we can think in terms of sinusoids, tones. For 1D, various frequencies are tones that we can generate. So we can connect with those. 2D, it's a little bit harder to connect with 2D sinusoids. But 1D, it is easy. So that transform has lived on. The separability symmetry facilitate representation and computation. Nothing to do with the filters, but with the transforms. Okay? So now was there something? No. Okay, let's look at the Wiener filter. The Wiener filter is a linear filter designed to minimize the mean squared error between the output and the input, which is not known. You have a distorted or some representation of the input that you obtained. It was degraded somehow, and you want to estimate the original. So you're not simply applying some filter and telling, well, this is a better picture than what you gave me, but you're trying to estimate in some optimal sense. The filter output is an optimal estimate of the original undegraded image. In what sense? Mean squared error sense. So it is also known as the linear minimum mean squared error, LMMSE, or linear mean square LMS estimate. A few different names for the same thing. It's a very popular filter. It's been around for 60 years in 1D and also in 2D. Not as long in 2D, but in my signal processing book, I have given the details of this derivation in 1D and applications to biomedical signals. So here we will use this representation G equal to F plus eta. We are considering only addition of noise. There is another representation with G equal to HF plus eta. H is an impulse response that is blurring the image, and then noise is added. Typically, when you acquire an image, there will be some blurring. My camera is not focused, there is some turbulence, and something is happening, so there will be some blurring. And then noise gets added due to all these instrumentation and the ambience. So G equal to HF plus eta, but then you require an inverse filter to remove the convolution H factor. That I have dealt with in a different chapter on image deconvolution and restoration. There is a Wiener filter for that also. But we won't go into that. If you're interested, you should refer to the chapter on deconvolution. But here we will look at noise removal only. The degradation is original image plus noise is what you have observed, or recorded, or captured, or given to you. So what you want to do is find f tilde. Tilde is used to indicate an estimate in some sense. Some books use the hat. I didn't use the hat because the hat is also used for the complex Kepstrom. So I kept the hat for the complex Kepstrom, and here we use the tilde to represent an estimate of f. It's LG. L is some filter. You apply some linear filter. We only know linear filters at this time, using LSI or linear shift invariant system representation, using all of what we have seen so far. So apply some filter G. You don't know what that filter is to get that estimate, f tilde. Now f and g are n squared by 1 matrices, formed a row or column ordering of the n by n images. And L is an n squared by n squared matrix in this formulation. And we have seen that formulation also earlier. The optimization criterion says minimize the mean squared error, epsilon square, which is expectation of f minus f tilde square. So the difference between your estimate and the original unknown image should be minimized in this sense, which is the square error. So it is called minimum mean squared error. Because the filter is linear, it's called linear minimum mean squared error filter. For the formulation to get the cross terms here, the energy of the error is defined not using the dot product, but as the trace of the cross product f minus f tilde, f minus tilde squared, tilde transpose. We saw this formulation earlier to get the energy of an image. So then you get all of these terms. You take this and expand, you get f transpose minus f tilde transpose and all of that. I won't read all of that, it's too much to read. And the transpose of f tilde is g transpose L transpose. F tilde is LG. Now the transposition is, each one is transposed and the whole thing is reversed. G transpose L transpose. G is f plus eta times L the filter. So now you expand each one of them. So you get all of these factors. So take each of these and put G's f plus eta there, and expand these. There is no G here, and take this, and you get finally this expression. Not finally, this f tilde transpose is this expression. Now, because G is f plus eta, you are getting these combinations of noise and signal, with one of them being transposed, and the noise also. Okay? So go back here. We wrote G equal to f plus eta, and f minus f tilde. F tilde is LG. G is f plus eta. And the mean squared error is that. It has all of these terms, these 4 terms. Expand each one of them using G equal to f plus eta. And f tilde as LG. And finally, each of these terms will turn out to be these quantities. So what you need to observe is that we have these combinations, the cross terms are coming now between the noise and the signal. Now we have a trace here, expectation and trace. In this matrix, you want to add up all the trace elements along the trace is the sum of all the diagonal elements, and you take the expectation, but then you can reverse that. The trace of a sum of matrices is equal to sum of their traces, so expectation and the trace may be interchanged. So take the expectation inside and apply to each of these quantities that you have. Expectation of FF transpose is autocorrelation. We have seen this earlier. We started with these definitions. And F tilde, you get phi f with L. F tilde is L. transposition is in the transform filter is included here. Fn and where is the other one? It's not here. Okay, this is 0 because f and n are assumed to be statistically independent. This is an assumption made in Wiener filtering, that the noise and signal, when you project them, the expectation is 0. The expectation of n is 0, of eta is 0. Expectation of f tilde f is that transposed. So L phi f. And this big expression we had here, you take this and that, and these cancel out. So you get only these two terms, L phi, L transpose, and the transposition of that, or rather with the eta, noise. Autocorrelation of signal, autocorrelation of noise, of the original, which you don't know. Expectation of eta, eta transpose is phi eta like that. Okay? You should work this out once and you will know. You have a question? No. No. Okay. Now you have the mean squared error, epsilon square, as trace of all of those put together. The autocorrelation function phi f is symmetric. The autocorrelation function of noise is diagonal because the samples are uncorrelated. The cross correlation terms will be 0. So the trace of phi f L transpose is trace of L phi transpose. So you get now the trace of autocorrelation of the original image, that with the filter, and that with the filter, autocorrelation of the noise with the filter. L is the filter you are designing, Wiener filter. So now the mean squared error is not a function of f, g, and eta that it was before, like this. It had a f and eta, but we don't know f, the original image. And you don't know eta, you don't have one noise, you don't deal with one representation or observation, you want the general statistics. What are the statistics? Phi f, phi eta, that's all, autocorrelation functions. So now, the mean squared error is not a function of the images themselves, but on their statistics, function of their statistics. And the statistics are simply autocorrelation function. So you need to differentiate that with respect to f and find out what is the optimal L. So differentiate with respect to L, and then take this partial derivative with respect to L. That has nothing. This has 2 phi f. This is 2 phi f. This is autocorrelation. So you get minus 2 phi f, 2 L phi f, 2 L phi n, and the Wiener filter is that. Autocorrelation of the original image that you don't have, and the inverse of this combination of the autocorrelations of the original image and phi of and noise. So the filtered image is phi f over phi f times phi f plus phi eta inverse times g, the given distorted image. So that's the optimal Wiener filter, optimized in the sense of minimum mean squared error, linear, assuming that the noise and signal are uncorrelated. And did we say anything else? No, that's all. Now, what we need are these quantities. We don't need the original image, of course, that's what we're trying to estimate, we don't know. Noise, you need to estimate the statistics now somehow. Autocorrelation function. And let's see how we can modify that a little further. So now inversion of that matrix could also be a problem. It's a large matrix, n square by n square. So inversion is easier if the matrix can be written as a product of a diagonal matrix and a unitary matrix, as we saw earlier. So the Fourier transform helps in that. So Phi eta is diagonal if eta is uncorrelated random noise. So it's already diagonal, no problem. What do you do with phi f? Here we start making some assumptions. In most real images, the correlation between pixels reduces as the spatial shift increases. In most real signals. If the signal is periodic, then the autocorrelation function will keep peaking whenever the same period appears. But in a real life signal, take a picture outside or any natural signal, voice signal is periodic, so not that. Some other signal, then as the shift increases, the autocorrelation function decreases. And very soon it will go to 0. So in most cases, autocorrelation function is a decreasing function, and for large shifts it goes to 0. So then phi f is banded. There are many, many zeros, and may be approximated by a block circling matrix. It's an approximation. Then if it is block circling, phi f is W, this capital phi f, W inverse, where phi f is the Fourier transform of the autocorrelation, which is the power spectral density function. Fourier transform of autocorrelation is power spectral density. Similarly, phi eta is W phi capital phi. This is the power spectral density of noise, W inverse. W is the DFT matrix. So now we have simplified in the sense we have diagonal matrices. And the diagonal matrices, as we saw earlier, contain the Fourier transform coefficients of whatever it is you derive it from. Fourier transform of the autocorrelation, that is the power spectral density. Fourier transform of the autocorrelation of noise, power spectral density of noise. This is power spectral density of the original process that generated the image, not the given image. So then, F tilde is this big thing now with the DFT taken out. W inverse DFT, phi f, autocorrelation of, the power spectral density of the image process, phi eta, power spectral density of noise, inverse is there. W inverse is the forward Fourier transform, and G is the given image. So take the Fourier transform of the image, multiply by this filter, take the inverse Fourier transform. So W inverse G is GKL, Fourier transform of GMN. Phi f, W inverse, this low, small phi f, W is SFKL, power spectral density of FMN. Phi eta is similarly S eta KL in array format that we are familiar with. Then the Wiener filter is this. F tilde in the frequency domain is SF over SF plus S eta G. This is how it is implemented in 1D also. We can, through a different formulation, we can get this in 1D that you can see in my other book on signal analysis. Or divide by SF, you get this. So this becomes a little easier for us to interpret. We know power spectral density and frequency domain functions a little better than autocorrelation matrices and the power spectral density as a matrix. So what does this say? When there is no noise, this is 0. And the output is equal to GKL. Nothing is done. So if there is no noise, the filter just passes the signal on a component by component basis. That is for every KL in the frequency domain. And wherever the noise is high compared to the signal power in the frequency domain KL, if the noise is large, this becomes large, and 1 over a large number, the gain is reduced. So wherever the noise is high, the gain is reduced. Wherever the signal is strong or there is no noise, the gain is equal to 1 or close to 1. So GKL is modified on a frequency component by component basis by a varying gain depending upon the noise to signal ratio in the denominator. So that is the Wiener filter. It depends upon the second order statistics of the processes generating the image population that you're dealing with, not that specific image, than upon single realizations. I mentioned earlier that it is, when we looked at the statistics of images, I said the probability density function and autocorrelation, they need to be computed with an ensemble or population of images of the same type. Mammograms or CT images of the abdomen of pediatric patients or male, female, and so on. So there must be a categorization. You don't mix CT with MR and other things. So if you're going to apply this filter to mammograms, you compute the autocorrelation function of a number of mammograms and average them and maybe fit a model, usually Laplacian model. Autocorrelation function decreases, Laplacian models fit well. And you just need the sigma, that parameter, the width of that function. One parameter that you have to store. If it is something else, some other function, a few parameters will help you save that function as the function SF or S eta. S eta typically is flat. If it is not flat, then you estimate it. So this is estimated from, let's say, a number of mammograms. And if you fit a model, the advantage is you just need the model parameters and say, if your input is mammogram, use this. If your input is CT image, use that. If it is some awkward function that you cannot model, just save that whole thing. As eta, you have to estimate noise. And you could estimate noise from the given images too by saying, okay, in this portion there is no image, so I'll take such portions from a number of images, take their autocorrelations and average, and then get the past spectral density or keep the autocorrelation. Typically it'll be flat. If not flat, whatever it is, parameterize that and save it. So for each application, you could save either the past spectral density models or autocorrelation models and apply the Wiener filter. You don't redesign the Wiener filter for every image of that category. So the gain of the Wiener filter varies from one frequency to another in accordance with the SNR, the signal to noise ratio or noise to signal ratio, as a function of 2D UV or KL, frequency space. Gain is high wherever the signal SF is strong as compared to the noise S eta, high SNR. Gain is low wherever SNR is low. Gain is equal to unity if the noise PSD is 0 at that point. The Wiener filter has nice theory. We study it in communication theory, DSP, and so on, in 2D also, but there are limitations. It is not adaptive. It is linear shift invariant filter with one impulse response or one frequency response for the whole image. For a mammogram, fine, there is some variation, but not that much. If you take a chest X-ray image, we have ribs and lung parts and the heart and so on, the frequency response is different. In CT image, there are more parts that are substantially different. So you need a spatially adaptive filter in such cases. Or you take an outdoor scene, your trees and vehicles and people and so on, then one filter for the whole image will not work well. It will give you some image. You may not be happy with the result. So it cannot adapt to the image and spatially. For the whole image, it is one filter. It can suppress noise, but it is likely to blur sharp features and edges. The noise will control the filter. But when you have sharp edges or nothing, or some other smooth variation, the filter cannot change. In the frequency domain, it is one shot point-by-point multiplication. In the image domain, it's a small, you can reduce it to a small mask and you are applying it as convolution. When you are moving the convolution mask across the image, it is the same mask being applied everywhere. So there could be some detail here and some other detail here, but the filter does the same thing. So it is not spatially adaptive. The design of appropriate signal and noise PSD models or autocorrelation models is difficult in practice, and if you use poor or inappropriate models, the results will not be good. They're optimal in some sense, but if the models are not right, then the filter is no good. The assumption is that the noise and image processes are second-order stationary processes. That is, you're only using autocorrelation and past spectral density. So mean and variance do not vary from one image region to another, which is not true in most cases. So the entire image is characterized by a single spectrum of PSD, and most real-life images don't satisfy these assumptions, and we need spatially or locally adaptive filters. So here is an example. The test image is one of those shapes images. We added Gaussian distributed noise. The image PSD, it's a little difficult to model this. I modeled it with a Laplacian function with sigma equal to 5 in the PSD, the past spectral density in the Fourier domain. And noise was modeled by a uniform function. So that's the original image, the noisy image. Sorry, I shouldn't press that. The Fourier transform of the original image, the Wiener filter. The Wiener filter, because the model is saying image plus noise, the Wiener filter to remove noise has to be a low pass filter. So it is a low pass filter, high gain here, gain reducing with frequency. That's the output, blurry. Noise has been reduced. Okay, compare with the original there and the noisy image to the right. And noise is reduced, but the edges have been blurred. So you want an adaptive filter. And there is an adaptive filter we will see next that gives this output, where the edges are sharp, but some noise is remaining inside these objects, as you can see. Inside this white box, you can see some patches of noise here. So adaptive filters also have problems. It's not like adaptive filters can do wonders. They can retain the sharpness of the edges, but inside it takes some time to adapt as the filter moves. And while it is still adapting, the results may not be good. We will see that filter next. Any questions about this? No?
Smoothness is because of smoothness. Because of what?
Because of the Wiener filter being low pass. You see in the second row on the right side, that's the Wiener filter in the frequency domain. The gain reduces with frequency. In high frequency zones, the noise is stronger than the signal. The signal actually has sharp edges. In this case, the images have sharp edges. But the model for the past spectral density I used is a Laplacian.
This is because of the second order statistics, something we use only second order
Yes, true. The Wiener filter uses only second order statistics, but the problem could also be with the model for the signal that I put in. I don't know how to model all of those shapes, right? There's a mixture of so many shapes. So I just put a Laplacian like that, which is not a good model. So it also illustrates what I said earlier. If the model that I put in for the autocorrelation or the past spectral density is not good, the result will not be good. How do I model the past spectrum of an image like that? I could possibly take a number of such images under noise-free conditions and average their past spectral densities and build a model and keep that. I could have done that. I could have generated a number of those pictures. We have a few, and average their past spectral densities and fit a curve. That is possible. I didn't do that. So if my model is not good, my output will be affected by that. I said the frequency contents of my signal decrease as a Laplacian function. In this case, they don't. Because I said that in the model, and I said the noise is constant at all frequencies in the PSD, past spectral density, then it says do a low pass filter like that. That has suppressed the edges, blurred the edges. If I can put a better past spectral density model, I may get a better result.
So in this case, we don't assume the desired output, right? So we don't assume any desired output, right? How we can compare with the least squares and this?
No, it's a least squares filter, yes.
Least square filters.
Yeah, it's a minimization of mean squared error. That's what we said earlier, right? We formulated the error and took the square value and the mean of that.
That F is the desired one. F tilde is
F is the desired. F tilde is the output of the filter. Okay.
But you said, right, the F transpose is the autocorrelation. Usually the autocorrelation is formed by the data matrix, right? Data using the data. Autocorrelation matrix is usually the data matrix.
No, this is expectation of F transpose is of the original unknown image, not of the given image. The given image is modeled as G is F plus eta. So the autocorrelation is of the original process that generated the image, not of the given image.
Here everything has to be estimated.
Yes. So that we don't know the original image, of course. So we need to build a database of clean images of that type and then get their past spectral densities or autocorrelations and average them. I didn't do that. I just put a Laplacian model. But that phi f is the autocorrelation of the original process that generated the image of the type we have on hand. F tilde is the output of the filter.
In communications, we assume the time being the data is available. Like desired is
that's different. That formulation is in my other book, where eventually you replace that with a shifted, delayed version of the input. You assume the signal is available, and then you say, well, I don't have the signal, so I'll take it to be the input with a delay.
Here the formulation is
It's different, slightly different. Yeah. The assumption is different. In my signal analysis book, I have used that definition, where it is assumed that the original signal is available, and you go through the whole derivation and then say at the end, well, I don't have the original. What do? I say the original is equal to the current signal with a shift. That is also a strange assumption to say, because the given signal is noisy. So the shifted version is not noise-free. That's an assumption made there. Here it's a slightly different assumption in this formulation. Okay? Any other question about this? Okay. You said 12:30, right? Okay. Okay, adaptive filters now. We will see a number of them. I'll go through one formulation and leave the rest. There is a local LMMSE filter, like a local Wiener filter. How do you make the Wiener filter adaptive on a pixel by pixel basis? But then you have to remain in the image domain. You can't go to the Fourier domain when it is not, not spatially invariant. If it is spatially variant, you cannot go to the frequency domain. So the adaptive local statistics based filter to obtain the same formulation of a linear minimum mean squared error, LMMSE is the same, but put another L that is local. Lee designed this filter. The degradation model is the same as before, G equal to F plus eta, but now we remain with this Mn because the filter changes with Mn. So data will be shown in this format to indicate the pixel position where you are putting the filter, and the filter depends on that. F is a realization of a non-stationary random field characterized by spatially varying statistics. Now it is generalizing. The filter can adapt to an image with different characteristics over space. So no frequency domain then. Noise process eta may be either signal independent or signal dependent, and non-stationary, don't care. It doesn't make any assumptions about that. So it says compute at every pixel location Mn an estimate f tilde of the original f by applying a linear operator to Gmn. What is a linear operator? You have two scalars, a and b, that are variant, spatially variant. So f tilde is amn gmn plus bmn, just ax plus y, linear. So not ax or not ax plus y, I should say ax plus b or something. So a is a coefficient, b is a coefficient. It's a bias at every pixel. This is just a multiplier, a weight factor. To minimize the local MSE, f tilde mn minus fmn square, and this bar says average in some way. It's not the expectation operator, it is some averaging somehow. And we will see that at the end. Okay, the formulation, just AG plus B. A and B are two coefficients, but they're all functions of Mn. So then this epsilon square is AG plus B minus F square, an average of that. Take the partial derivatives with respect to A and B and set them to 0. So take the partial derivative with respect to B, so you get this quantity. That bar remains undefined. And then you get B is F bar minus A G bar. I won't read the Mn. And put that and get epsilon square, differentiate with respect to A, set it to 0. You get that quantity. And now this has so many things here. You get all these cross terms. You have to work out all these terms. G, F bar, G bar, F bar, G bar, F, and all those things. And here AG and AG bar. So now to simplify it, you say, okay, G minus G bar. G bar is like a mean, mu. So the signal minus mean square is variance, averaged. That is like expectation, let's say. So this is variance of G. G is the given signal, but at the local point, Mn. That's a local variance of G. And G minus G bar, F minus F bar is sigma Fg, the covariance between the two of them. So this says then Amn is sigma Fg over sigma square G, a ratio of the covariance to variance. So F tilde is F bar, you put them all together, sigma Fg over sigma square G, G minus G bar. So these are statistical entities based on some local window, because you have to make them a function of Mn. It's not computed for the whole image or population. It is computed for that image, the given image in that window. So you are substituting later on expectation and statistical processes with local averages. We have done that with time signals, and the time temporal statistics and spatial statistics. So now we are using spatial statistics, local, not for the whole image. F bar is a mean at that location. But F is the original, we don't know that. Fg, we don't know that. F is unknown. So we need to manipulate this further. So the true statistics of the original and corrupted images, as well as their joint statistics, sigma Fg, are unknown in a practical situation. So Lee said we will estimate them locally in a spatial neighborhood in the given image itself. And then formulate a local Wiener kind of a linear minimum mean squared filter. So use a rectangular window at that location. 2p plus 1 times 2q plus 1. So it's an odd sized window, but the window size could vary to be adaptive. So it's not 3 by 3 or 5 by 5. We'll let it be a rectangle of some size to be defined later. So mu g, the mean of g, is given by the average of g over that window. Okay, it's a big equation, but it's just averaging of g, given image, over that window. Centered at mn. So it changes from pixel to pixel. Sigma square g is g minus mu g square and averaged. Okay? Local statistics. The filter parameters are functions of space. They are space variant. So it is an adaptive filter that is space variant, and hence you cannot go to the frequency domain. So now f tilde is mu g, sigma square g minus sigma square eta divided by sigma square g, g minus mu g. All functions of mn. So this is also known as the Wiener filter or local Wiener filter. It looks like the Wiener filter, but it varies with the indices mn. It is locally adaptive. MATLAB calls this the Wiener filter. LIM also calls this the Wiener filter. It's only because of that minimization of the squared error. Otherwise, it has nothing to do with Wiener. So there is some similarity. But the interpretation is slightly different, as we will get to the end. So this LLMMSE, local linear minimum mean squared error filter, is spatially adaptive and non-linear because of the space variant estimation of the parameters. Depends on the image, so if you add two images, these statistics will be different. Okay, let me get to the interpretation of this. This is the filtered image, f tilde, estimate of the original. Mu g, g is the given image. It's a local average in a window, whatever size you choose it to be. G is the given image at that pixel, minus mu g, subtract. This is the weighting factor. Sigma square g, the variance of g, the given image at that location, minus sigma square eta mn, the variance of noise at that location, divided by sigma square g. Sigma square g you can compute from the given image. How do you estimate sigma square eta as a function of space? That is another question. Typically you would assume that to be constant. You would assume the noise is the same all over the image. So if you can measure the noise from somewhere in the image and get its variance, get a bunch of pixel values from somewhere where there is no signal, and say, okay, that's my variance. And I'll just assume the noise is the same throughout the image. That's a reasonable assumption. It is not reasonable to assume that the signal variance is the same throughout. That is not reasonable. But noise, it's okay. There are other ways to estimate that also if you want as a function of space. So this is some factor, let us say. You could say by removing the variance of noise from G, which has signal and noise, you are getting an estimate of sigma square f, the original, variance of the original, in a way, divided by this. So this, what is mu G? Mu G is a local mean, which is like a low-pass filter version of the given image. When you take the local mean, the 3 by 3 mean filter we saw, it is a local mean, and that is a low-pass filtered output of the image. So this is a low-pass filtered output at that location using a little window. And what is this? The signal minus the low pass version. 1 minus low pass is high pass. So this is a high pass version. Edge enhancement is being done here. So this is blurring, this is sharpening. Low pass filter, high pass filter. You are getting a combination of low pass and high pass filter controlled by this gain factor, which changes with the local statistics over the entire image as you go, with the filter window running across the window, across the image. So that is how it is adaptive. It takes a combination of a low pass filtered version and a high pass filtered version of the given noisy image and gives you something with enhancement with noise control. So where you have sharp edges, it will try to preserve the edges. Where there are no sharp edges and only noise, it will suppress noise.
This is done by pixel.
I'm sorry, you have to speak up a little.
No, this is done by pixel by pixel.
Yes.
Pixel.
Yes.
Pixel by pixel value.
That's why the filter is, everything is written in terms of MN.
And why can't we take like a window and
Yes, these are all computed, these are computed using Windows.
But what is the typical window size?
That's up to you. 2p plus 1 times 2q plus 1. You can let that window change. We will see that. You can let the window adapt.
If you take a bigger window, the statistics will be changed.
Yes.
Non-stationarity comes into picture.
This is non-stationary already. This is not
We assume stationarity and we apply linear feature. That's what
with the Wiener filter. This is not stationary. Here we didn't say, we said specifically the image is non-stationary. Even the noise could be non-stationary. So there is no stationarity here. Everything is varying pixel by pixel. And the statistics are estimated using a window, local window of some size. We didn't say what the size is. Actually, we said, I think, here. It is 2p plus 1 times 2q plus 1. Whatever p and q you want. But there is another filter we will see where the size of that rectangle is adjusted. There is an adaptive rectangle window. And we have our own adaptive neighborhood filter. So this can be changed as you wish. But it's a local statistical measure. So it is non-stationary. It is non-linear. It is adaptive. Okay? There is a matrix derivation. My colleague Mihai in Bucharest, he was with me for some time. He gave me this. So you can go through that same formulation using matrix representation. F is AG plus B, and go through all of this, and finally you get the same thing like this. Low pass filter, high pass filter, that's the gain for the high pass filter. I'll let you read that later if you wish. So there are some variations on this. We'll skip that. In some variation, that window is split. The window that you use to compute statistics may be split vertically, diagonally, up, down, left, right, and so on, depending on local edges. If there is an edge present, this method, refined method, says don't compute the statistics over this entire window, but use only one part and compute the statistics using that part, and don't blur across edges. So you have to estimate the presence of an edge and its orientation by using gradient operators, which you can do, of course. And then the window of some size, here we have assumed it to be square so we can show the split. You use statistics from the side where your pixel is sitting, or an appropriate size, or part of it. There is another version where these sigma values are updated. Sigma eta of the noise is updated. I won't go through that. And we will stop here, but let me go back and show you that output. The images have been put together for comparison. So we have the the original and noisy as we saw before. The output of the fixed Wiener filter, but my signal or the original model of the original pass spectral density is not good. It's a Laplacian, it's not good. In some cases I have done something and I could say I didn't want to spend too much time to find a better model, or I also want to say what happens if you don't use an appropriate model. If my model is not good, I may get a bad result, and I don't want to blame Wiener for that, of course. But the adaptive one is this. So there's a big difference. Sharp edges are maintained. There is some smoothing compared to that. Compared to noise here and noise inside the white big square or that triangle. A little smoother. Edges are sharp, but there are still some noise samples remaining. The filter needs some space to compute the statistics, and as you are moving, the statistics are changing. But some parts it cannot adapt well. You need to have some local stationarity for the filter to adapt. Then if the statistics change slowly, it'll work. If the statistics change rapidly, then the filter may not be able to adapt. Still, this is better than that. Let's look at the RMS value. What does it say? Wiener is 52 and local is 13. So this certainly has lower mean squared error. E is a Wiener filter, that's 52, and this is 13. So the error is reduced compared to the noisy one. How much is the noisy one? 19. So the Wiener filter, because of blurring, has actually increased it. But I would say that's because of an inappropriate model I have put in. Okay? 12:30. Any questions before we go for lunch? Thank you.
For example, with G shapes are there. Natural image.
Yeah, true.
Yes.
Do I have any other example? I may have some examples later.
Capsicum images.
Yeah, those capsicum peppers images and so on. That I'll show you that. There are some real images. Well, they are also not real. They are stacked. So if you want, you can try that. I don't have any Wiener filter applied to medical images. I do actually. In a chapter on the nuclear medicine restoration, I do have some. If you look at the restoration chapter, I won't go through that, but if you're interested, I can show you. We have Wiener and a few other filters, including Kalman filter for nuclear medicine images. So I can show you that later if you wish. These images, yes, true. We synthesize them that way, we design them that way in order to demonstrate the effects where filters work and where filters fail, where you get good results and where you don't get good results, and where you have these sharp edges, they pose problems. Will you have a real image like that? Maybe. If I'm taking a picture of this, there are these lines and sharp, all these tables and metal parts. There are some rapid transitions. So you may encounter such edges in sort of real images. So what's a real image? Maybe just my face just this much, but even then I have all these black and white parts, and if you apply some other makeup, then there'll be more rapid transitions. So yeah, there are such transitions in real life images. If you take only this much, maybe there is no variation. But those are sharp. No questions? Okay, let's take a break. What did you say? 1 hour break?
1 hour break. We'll be back at 1:30.
Thank you.
Again, language is in the same areas as there's some power interruption problem. Others can keep that open.
I forgot to say this earlier. I'm sorry for the informal appearance. Yesterday I came with my tie and jacket. When I give lectures, I always have my tie and jacket on. But I have not given lectures in this atmosphere. Everything is sticking, and I learned my lesson yesterday. So I hope you don't mind this. I was asked about Wiener filtering of real images. I showed only the synthesized images. So this is from our own research. It's in chapter 10 of the book. We will not go into image deconvolution. But these are SPECT images, single photon emission computed tomography images. And this is of a phantom. I'll start with the phantom image. The phantom is a tube with a solid rod inserted, and the open space is filled with the radionuclide material. Thallium or technetium, it's not mentioned, it's in the book. So the cross section is like a donut or a udinvade with a hole there. So this is the original image with a lot of noise. Each image is only 64 by 64 pixels. Ideally it should be like that. It's not that, it should be a circle. But this is on a discrete grid. This is after Wiener filtering of this image. This is another filter called the pass spectrum equalization filter. So this Wiener filter is not the same as what you saw. The degradation model is G equal to HF plus eta. There is blurring and there is deblurring here. There is inverse filtering, but with the Wiener filter. Now, this is a 3D image. I'm showing one section. It's a tube lying flat on the table, and then you're taking a section. A tube with a solid rod, and the rest is filled with the radioactive material. Gamma ray photons are emitted. When you take a projection of that, and you get the tube in different angles. You don't go all the way around in cardiac imaging, you only go 0 to 180. Now restoration is possible by taking only this one image in cross section and restore that. That is called post-reconstruction. After tomographic reconstruction, you have a 2D slice. If you want, you can try in 3D. But we didn't do that. Instead, we said we will do restoration of each two-dimensional projection image separately first. When the scanner goes around, multiple projections are obtained, two-dimensional images of the body, and then the sections are computed. So we can restore each of the 2D images first, and that's better because you take blurring in the other dimension into account. And you can incorporate the dependency of the point spread on the distance between the collimator, the photon counting device. Before that there is a collimator, and the body going around. So we call that pre-reconstruction restoration. If you restore each of the projection images first and then do the tomographic reconstruction and get the cross-section, and then CT, you get this. Compare that with this. This is Wiener filter applied to each projection image and then reconstruction, and a few other options. So these two are Wiener filters to this image, and this is to each projection image. One of my PhD students did that, and this is of a patient. This is imaging of the left ventricle. This is one of the projection images at some angle. So for this type of imaging, they go 180 degrees here, not the other side. From here to the other side, 180 degrees. And that's one of the projection images. The heart is here. The abdominal organs also have taken up the radioactive material. There's also the intravenous tube there. Well, you're interested in this part, and that is reconstructed in some 3D, and some other planes are cut. So these are the images corresponding to that phantom I showed. If there is a blocked part, then that part of the left ventricle is not getting blood supply due to some blockage. So here we have I need to check which is which. Post-reconstruction using the Wiener is B. A is the short axis spect. This is the original. This is after Wiener filter. Pass spectrum equalization METS filters. But if you apply the Wiener filter to each projection image, which is that 2D image you saw, and then do reconstruction, we get this. Certainly this is cleaner than that and sharper. So this is a real life patient's image using the Wiener filter. And we have done the Kalman filter. In these cases, the images are fairly small, spatially. When you consider the liver and the abdomen, then the object is larger, and you need to take into account spatial variation of the point spread function. And then we have used the Kalman filter. And I won't go into that because we are not looking into the Kalman filter. But just for the Wiener filter, I wanted to show that. We tested that with the phantom that we built ourselves in our lab, and then with real patient images. This is another phantom. This is another phantom made by a company where there is a drum and a number of tubes here. If it is white, it means it is hot with the radioactive material in the tube. If it is not active, it means there is no radioactive material in the rest of the drum. And there are multiple pairs of these tubes. You don't see these at all. They're all blurred out and lost in the noise. There are two big tubes here, and there are multiple tubes here in pairs. After restoration, you start seeing some. And then some more. 1, 2, 3, 4, 5, 6 pairs of tubes, and it's cleaner. D, which is which? B is Wiener filter, this is pass spectrum equalization, this is the Kalman filter. Just so that you see application to real life images. This is the liver and spleen. Before, this is the original, and this is using the Kalman filter. Sharper edges. Are these real? We don't know. The radiologist looked at these images and said there is some enhancement, but we can't quantify it. They did not do any diagnosis and diagnostic evaluation with multiple patients. We didn't have the resources to do that. Another case, the original, and this is with the Kalman filter. But here, the model is G equal to HF plus eta, blurring and noise. So there is deblurring and noise control. If you want to read more about that, you go to chapter 10 in the book. I don't have lecture notes for this to give you. Okay, let's go back to our lecture material. We saw the Wiener filter and the adaptive LL and MSE filter. Now there are a few more adaptive filters where some parameters are modified as you go pixel to pixel. The adaptive 2D LMS filter, least mean squares filter, is like a fixed window Wiener filter. The window size is fixed, but the filter coefficients vary. You apply this in the space domain. But as you go pixel to pixel, the coefficients within that mask of the filter will change, will adapt to what is present in the image. The adaptation is based on the method of steepest descent, and it tracks variations in the local statistics of the given image or signal. In my signal processing book, you will see the same filter for biomedical signals. It does not require any a priori information about the image, statistics, and so on, correlation and all that. There's no averaging, differentiation. It just keeps on adapting. There are limitations. It's a nice approach, but it doesn't always work very well. So assume we have a causal FIR filter, finite impulse response filter, WLPQ. L is an index related to the position in the image. Mn are the pixel locations, PQ are the locations of the filter coefficients. This is the convolution integral on WLPQ. G is the given image, n minus p, n minus q. And at output f tilde mn. So L is the current position of the image as you move from along one row, column to column, and the next row, and so on. L is given one index, m times capital M plus n. M is it's an m by n image. So as you go one row to the next, this is a running index, but one value, not two. So L goes 0 to mn minus 1 for an m by n image. So the filter coefficients for each pixel location are determined by taking the filter coefficients at the previous location and modifying them. And what is the modification? You take WL plus 1, the new filter for the current pixel location, is given by WLPQ, the filter for the previous location on the image, minus mu, this gradient operator nabla E square, L, where mu is a scalar that controls the rate of convergence and stability. You don't want the filter coefficients to vary rapidly. If you make the constraint too tight, then the filter will not be able to adapt. If the filter changes rapidly, there could be instability. So convergence and stability need to be controlled, and that's this factor mu. EL is the local error signal, and nabla is the gradient operator with respect to WLPQ. We will see how to get that. So E is defined as D minus F tilde, where D is an approximation to the original FMN. Dr. Narasimhan was asking that question. In 1D, this is how it's been derived, even for the Wiener filter. That you assume that the original image is known, and then you say, well, I'll make an approximation, and I'll take it to be a delayed version of the current distorted image that you have on hand. So DMN is an approximation to the original. And what is DMN? You take the current GMN, the distorted image you have, with a delay of one samples, one sample before and previous row and previous column. Why? I don't know if that's a good approximation. That's one of the assumptions made, but that could be noisy too. How can that one sample before be a good estimate of the current pixel without noise and without distortion? But that's the assumption made. So WL plus 1 PQ is the current filter, the previous filter, plus 2 mu, this error, and GM minus P, N minus Q. So that's the model. It's a recursive equation defining the filter coefficients of the pixel location L plus 1, the new location, with reference to the previous one. So here is that shapes test image. It's a different one. We have multiple versions of this. This is Gaussian noise added. This is the 2D LMS filter. And this is the next filter that we will see. So look at just this one now. The other filters will come later. So from there to there, there is limited reduction of noise. The edges are retained quite well, but there is still a little bit of an overall blurry appearance. So I wouldn't rank this filter very high. RMS 14, actually it increased from 14 to 15. The error with reference to the original. So the output of this depends upon these parameters. How do you control these? So it's a bit difficult to optimize that any further. There is another adaptive filter called the adaptive rectangular window, where the window itself is adapted. How big do you want that window to be? To compute the local statistics, we said 2p plus 1, 2q plus 1, rectangle window. What should be the size of that? Here they said adapt it. Let it vary in a uniform area where there is no noise and no structural information. Make the window as big as possible, use as many pixels as possible, and get a good estimate and suppress noise. As the window comes here, there is some edge, some information about the signal. Then you reduce the window size. So as you move here, window size is reduced and adapted so that you don't mix. You don't take a big statistical average over a large area. So this was proposed by Song and Perlman, and then there are other references from their group. It is assumed that the image processes have zero mean, which is not true, so you subtract the mean. Given an image, take the mean and subtract it, store it because you want to add it later. Otherwise, you will have negative values and edges only, and you don't want that. So f tilde mn is some weight alpha mn times gmn. Previously, we had a, g plus b. The plus b is removed now. So you want to find alpha mn at each pixel using some criterion, minimum mean squared error, for example, as in the Wiener filter, or something else, but they use the same. EMN is f minus f tilde, f minus alpha g, similar to what we have seen before. So minimization of mean squared error requires E to be orthogonal to the image. So expectation of f minus that times g should be equal to 0. That's the requirement imposed here. So then solving for alpha, you get this. You have seen a similar ratio before in the Wiener filter. Now it is variance of the original image, variance of the original image plus variance of the noise. So this is the variance of the given observed image. Because a noise is of zero mean, the a posteriori mean, mu g, is equal to the a priori mean, mu f. So the mean of the given noisy image is equal to mean of the original. So then f tilde mn is mu g, not mu f, but now you say mu g. And this factor times g minus mu g. So this is similar to what we had seen earlier. A low pass filter, a high pass filter, and a weighting factor. Okay? Some small variations, but the basic idea is the same. How do you implement it? You assume that pixels in the immediate neighborhood of Mn are samples from the same ensemble. So there is stationarity. Global non-stationarity is now considered to be locally stationary. The whole image is non-stationary, but in small portions it is stationary. That's the assumption in that window. And ergodic. So you replace ensemble statistics with spatial statistics. So if we determine the size of a neighborhood in which the image values have the same statistical properties, the sample statistics can approximate the posteriori parameters in that equation we saw. So you need to identify the size of a stationary rectangular region within which to compute the statistics for that pixel. The window size changes according to a measure of signal activity. So they define some signal activity. Signal means image structure. So the adaptive rectangular windows were defined to be of odd length LR in row and LC in the column direction. So LR is 2NR plus 1 and LC is 2NC plus 1 to represent they are odd. So you go minus NR to plus NR, minus NC to plus NC to take the local mean, just adding the pixel values in the window. And local variance is the pixel value minus minus the mean and the summing and averaging. Right? You have seen these before many times. Now, these are varying pixel to pixel. This is varying pixel to pixel as you filter. Sigma square f, the variance of the original image is the variance of the given distorted image minus variance of noise. We said earlier that sigma square g is sigma square f plus sigma square eta. Now it's the other way. So you are estimating the variance of the original signal, original image, by subtracting the variance of the noise from the given noise image. So you need to know noise variance. As I said, noise variance you estimate somewhere else from some part of the image that has only noise. Then the estimate is mu g plus g minus mu g. The same thing, low pass, high pass, with this weight factor. Sigma square f is given from that. Sigma square eta must be independently estimated using some other mechanism. These are computed for every pixel. LR, LC, NR, NC, mu g, sigma square g, sigma square f. To vary the size of the window, they recommended a signal activity SRMN in the row direction. R is row, where they took a kind of a variance in the row direction. This is variance. This is mean in the row direction only. Minus nr to plus nr, m plus p only, n remains the same. Minus sigma square eta. So this is, you're comparing the signal variance, subtract noise variance, and the mean is local in that row direction only. And they said nr is reduced if the signal activity is more than some threshold, or it is increased if the signal activity is less than the threshold. And the threshold was defined as some factor kappa times sigma square eta, noise variance, divided by LR, the length of that window. So there is some factor kappa to control. The same is done for the column direction, similar. So the rectangular window adapts by becoming broader or taller as you go pixel to pixel, and the local statistics are computed for every pixel as the window moves. I'll go through this filter and then we will go back and look at the results. The adaptive neighborhood filter is our own design. When I went to Canada as a postdoc fellow long ago, 44 years ago, 1981, I went as a postdoc fellow. My supervisor, Dr. Richard Gordon, came up with this idea that we should have adaptive filters that don't depend simply on fixed windows or populations of pixels as you move the filter from pixel to pixel, but instead the neighborhood of pixels that you use at every location must adapt to what is present in that location. So we call that an adaptive neighborhood. Not rectangle, it could be of any shape and any size, depending on what is there. So if you're processing a pixel here, it should take this same, approximately the shape of that. If you're processing a pixel here, it will take the pixels there. You don't mix an object with the background. That's the whole idea. But there's not always a background and an object clearly. In a mammogram, there are so many parts. But there are some regions that you can identify, like calcifications and ligaments and ducts and so on. And there are some background tissues, fatty tissues and others. And you don't want to cross their boundaries. Don't blur across boundaries. He wanted to call it pixel-independent processing. That is, we are not processing pixels, we are processing regions or objects in the image. But there were other papers, other methods called region-based or, what is the other one I said? Object-based processing. So we could not use those names. So we said pixel-independent, and even that was criticized, so we simply said adaptive neighborhood. So a variable size, variable shape neighborhood is defined or determined rather for every pixel in the image. It's expensive computationally. The adaptive neighborhood grown for the pixel being processed, which we call the seed, contains only those spatially connected pixels that are similar to the seed. There's some similarity like a distance measure. The neighborhood does not grow over edges but overlaps a stationary area. The statistics computed using the pixels inside the adaptive region are likely to be close to the true statistics of the local signal and noise components at that location. So when I'm processing here, I can grow a region that is like this, however big I want, taking all the background. It could be of some shape and size. But I can put limits. I don't want 10,000 pixels. I'm happy with maybe 100 pixels. That's enough to compute statistics. So even though I can grow a huge region for a pixel here, I may stop there. Whereas for this, I'll grow a region that takes only pixels within that object. So region growing. For every pixel, you have to grow a region and find what is the local region, what is the local object. So you compare the 8 connected neighbors GPQ and the seed GM. GMN is the filter, the point where you are filtering. GPQ are the neighboring pixels, but not just left and right and top and bottom, but somehow connected. The connectivity is determined by, the similarity is determined by this DPQ, just the difference. And we have some modifications to that I'll show later. So pixels GPQ having DPQ less than some threshold and spatial connectivity will be included in the region. The procedure continues by checking the neighbors of this new pixel you added in the neighborhood and take their neighborhood and ask, can I include them and their neighbors? And all connected neighbors are checked. Until you hit some boundary, you cannot grow any further. So adaptive neighborhood is grown for each pixel in the image. That makes it expensive. Now, once you have this region, in some types of filtering, you may want a reference around that. So you put a ribbon around it of the same shape and take those pixels to represent the background around that region. There is the notion of redundant seed pixels. When I have a region grown from here, many pixels here may give you the same region again and again. So we say once you grow a region, if you use a simple criterion for inclusion, then you can say that if I were to take another pixel from that same region, I'll get the same region as the adaptive region. So all of those pixels will get the same output. I don't have to repeat the process. So we call them redundant seed pixels because you would get the same output if you do the entire process. It depends upon the threshold used for region growing and all the conditions you put. It cannot be done always. So here's an example that my student William Morrow developed, a nice illustration coming from Canada. That's a mountain in the Canadian Rockies. I don't remember its name. There's some snow on the mountain there, and that's the pixel from where region growing is starting. And these are the gray pixels are the region pixels being included in the adaptive neighborhood. The black pixels have the same value as the starting pixel, so they are the redundant pixels. And if you grow again using those pixels, you get the same output, same result, same region. So you don't have to repeat. So the region is growing, and here it has hit the boundary. It's not growing anymore in that direction, but it grows here. And that's the final region. And around that, in dark gray, there is the ribbon, which will be the background for that region. So the starting pixel was somewhere there. All these black pixels have the same value as the starting pixel and are redundant seed pixels. These gray pixels are included in the region, and there could be some holes here that don't belong. Some pixels may not belong, but they are inside. We don't use them in computing the statistics. and that is the ribbon all the way around. You can define a certain thickness and obtain it by dilation of the boundary. You do that for every pixel. So for a pixel somewhere here, you may get a region like that. For a pixel here, you may get a region like that. So then what do? You compute statistics. Why 3 by 3? But the basic question we asked is, what is so special about 3 by 3, 5 by 5? They're not sacred. And similarly, why rectangle? Why not circle? Why not something else?
Easy grade is 3 by 3.
What's that?
Easy grade is 3 by 3.
It's easy, yes. I said it's not sacred, but 3 is sacred. Yeah, there are many things 3. So that's the basic question we asked. Why square and why fixed? 3 or 5 or 7 or something. And why odd? Odd is for centering. Here it is not centered. It could be any shape and it could go somewhere else. But because of the constraints of spatial connectivity and similar gray level that we impose in region growing, the assumption or the model is that all of these pixels belong to some object with similar properties. So when you compute their statistics of those pixels, then you are getting the statistics of some signal component, image component that is present at that location. But that object has some spatial extent, so that could apply to other pixels in the same object. But the objects are not constant. So for another pixel in the same object, you may get a different region. It's not segmentation. But for every pixel, you grow a region. But under certain conditions, a number of pixels with a given region may get the same result. So here is one of our shapes image, and with Gaussian noise added, and 3 by 3 mean, 3 by 3 median, adaptive neighborhood mean, adaptive neighborhood median. There's a little bit of blurring. Now we compared with 3 by 3. It's unfair. We have compared with others later. So the original and noisy, 3 by 3 mean and median. Obviously the 3 by 3 mean is blurring. 3 by 3 median may have caused some distortion. It's a little hard to see here. And the adaptive neighborhood mean and median. There are still some regions where, some parts where the region growing has not done well. But there is no blurring of edges, even with the mean. And one of my postdoc fellows, Raman Parangape, he came up with the idea of noise subtraction. Instead of estimating the signal, he said we will estimate the noise. It just reverses the process, that's all. So this is similar to the adaptive rectangular window LMS formulation. So there is not much to do here except that eta is estimated, signal is estimated eta tilde as alpha GMN. But then it leads to something very similar as before. F tilde is G minus eta tilde, and F tilde is beta GMN, but beta is 1 minus alpha. So the rest is the same. So I'll skip all of that. In the end, you get a result that is very similar to what we have seen before, but 1 minus that. So let's skip that part. There's a flow chart, but I think I have already explained that. So here is another image. Is it blurry? To me, it looks a little blurry. You said okay, but it is a little blurry. So here is a part of the peppers image. This is part of a pepper, the edge, noise added. That's the seed pixel. This is the region grown. With some adjustment, this white is the adaptive region. It has not crossed the boundary. And these pixels are not included. There were some pixels inside the region that later on were included. Another postdoc, not postdoc, but he was a visiting researcher, Mihai Chuk, from Romania. He spent some time with me and modified the region growing procedure and put some constraints so that you don't get huge regions. We don't need such a big region. So if we get about 100 pixels or so, it's enough. So we stop region growing there. But on this side, it stops due to the conditions implied. Conditions imposed, rather. So after filtering, we get this from there to there. This is only a part of the image. The whole image was filtered. So this is the noisy image. This is the filtered image. So this is with the test image, the clock image. So 3x3 mean, median, the refined LLMMSE filter, and sorry, not that. D is the refined LLMSE filter, and there was another noise updating recursive Wiener filter that we didn't talk about yet. This is the adaptive neighborhood filter. So this is the noisy original image. We didn't add noise. That's the way it is. That is 3x3 mean, 3x3 median. You had seen that earlier. So we have good noise reduction compared to that, and all of these numerals are preserved better compared to the 3x3 filters. The others are not bad. So Mihai did many of these experiments comparing various basic filters and advanced filters, all the adaptive filters. I don't have to go through all of them. You could go through them later. The peppers image, this is another commonly used test image. The noise level is too low. Let's skip that and so this is Poisson noise, where you can see a little better the noise that is present. And C is refined LLMMSE, the noise updated recursive Wiener filter. E is adaptive neighborhood. This is our mean filter, and this is our adaptive neighborhood LLMMSE filter using adaptive neighborhoods. We showed that our methods gave lower RMS errors, cleaner images for various types of noise with not much of blurring of the edges.
Question here is like, it's my personal feeling also. When we see MSC 85.32, when we do research and if we get some result, what happens is 85.3 and 86 point something. We don't know whether our result is very much improved or not.
Correct.
If we get a little bit increase in the number, we tend to publish that.
Yeah. The question is, how many decimal places will the result be relevant? Is 85 better than 86? That's like 1 point some percent. It's not a huge difference. But perceptual evaluation matters more, and it's been shown that mean squared error and RMS don't agree well with human perception. There are other measures. So look at this and see if you can focus. So let's wait for it to be focused. This is the salt and pepper noise illustration. So we showed this, and Mihai did a detailed study, and we have all these measures. I don't want to go through this table comparing error measures. We will skip these and maybe just look at one of these pictures. You tell me from there. By the way, that itself is a good filter, low pass filter when you blur the lens. Really, yeah. Oh, you see there you have a zoom there. That's good. let me put up text here, there. Let's look at the text. Oh, blur, okay.
This is a maximum.
Okay,
Okay.
Better.
better? Is that okay? But if you look at this image, some of them are blurry, so it's hard to judge. And it's, okay. You may take these files and zoom and take a look in detail yourself later. So this is with salt and pepper noise, and C and D are 5x5 mean, 3x3 median, and adaptive neighborhood mean and adaptive neighborhood median. So we have shown it works reasonably well with multiple types of images and also with color images in a different paper. And there is a table of mean squared error values. I won't go through that table. It's not necessary. There are a few other examples where multiple methods have been compared. The clock image, you have B is 3x3 mean, 3x3 median, refined LLMSE, the noise updated repeated Wiener filtering, and the adaptive neighborhood LLMSE filter. So in this way we compared and did an analysis. And evaluated multiple filters. But eventually, the user in the application domain needs to assess them. We use the error measures, but error measures are not correlated with visual perception. These measures. There are other measures in color images using other domains. The LUV and LAB domains have been shown to be better correlated with human perception, and error measures defined in those domains have been shown to be better correlated with human perception. But in grayscale images, we don't have any other representation. We just take the LMS and mean squared error. I mentioned earlier that there are the Laplacian errors and then the visually perception, human visual perception related filtered error measures. So you could use those and compare, but we haven't done that. It all depends upon which model suits the application. Okay, at the end of each chapter I have given some applications. So there is a bit of a repetition in the sense I showed some examples earlier with synthetic images. Now I show the application. Multi-frame averaging, I mentioned earlier, ensemble averaging could be done to reduce noise. In confocal microscopy, you use a laser beam to scan a sample. It could be a biological specimen. There could be some thickness to it. So a laser beam is scanned, and it finally focuses on certain planes, and the sample is tagged with the fluorescent dye, and that gives out light at a certain wavelength. The use of coherent light obviates the blur caused with full white light, the full spectrum. So you use only that specific wavelength of light because the laser beam is having just that frequency. Laser excitation causes the dyes that have been applied to the sample to emit light, that is fluorescence. So the sample fluoresces at a particular wavelength. And using multiple dyes to stain different types of tissues and structures in the same sample will lead to a color image with different parts emitting different color when triggered or excited by the input laser beam. So the confocal microscope uses a pinhole and then focuses on one plane. The sample could be thick, a few millimeters, not that thick, but a few millimeters, and a certain plane is focused, and then by changing the focal plane you can get multiple slices. You don't do 3D really, but you could stack up those slices. The light from other planes are blocked. light from various other planes. Only one plane is focused. A photomultiplier tube is used to amplify the light, and that could cause some noise amplification. So you average, you take the image over a certain number of time and certain window of time and take a number of images. A scanning mechanism is used to raster scan because it's a single laser beam. You have to scan the sample and then assemble the image. The sample step could be of the order of 0.1 micrometer. That's the resolution you can get. The distance also matters. The planes, between the planes, the separation could be of the order of 1 micrometer. And it is possible to assemble them to get 3D, but I didn't see any 3D examples. What I got is just one plane at a time. The sample I have here is a set of cells from the nucleus pulposus, which is the portion between the intervertebral discs, or the discs between the vertebra and the central portion of the discs, scanned using a laser beam with that wavelength of 488 nanometers. The red dye that is used gives radiation or light in the frequency of our wavelength of 585 nanometers, and that corresponds to the nuclei of the cells. The green dye in the band of 505 to 530 nanometers shows the filament structure. The focal plane thickness is about 1 micrometer. Now if you take just one image, it'll be noisy. If you take multiple frames, the sample is fixed. It's a biopsy specimen, so it's going to be there. But if you scan it too many times, you're depositing laser energy into that. There could be local heating, and the sample could change its characteristics. If you keep scanning, it could lose its capability to fluoresce, or it could develop autofluorescence. So there are other complications. So even with a fixed specimen, you cannot do this a million times. So you can acquire a few images and average. So here we have the red dye and the green dye showing the filaments. Here you see the cell structure, cell nuclei, the actin filament structure, and when you combine them, you get the color image. It's an artificial color image due to the excitation with the laser. This is the light emitted from the sample by fluorescence. The width of the sample is 145 micrometers. Let me see, was this averaged? Each image was averaged over 8 frames. So here we have just without the color, and let me read the single frame acquisition and another single frame, averaging of 4 frames and 8 frames. One frame, another frame, average of 4, average of 8. So if you compare 1 with average of 8, you see some reduction of noise. The details are not any a little sharper, but the noise is reduced. So these are real acquisitions of a real sample. The noise is inherent in the process of acquiring the image, and also from the photomultiplier tube. When you amplify the signal, noise is amplified. Okay? Now when you filter a single frame acquisition image, suppose you cannot acquire multiple frames, you could try filtering one frame, 3x3 mean, median, 5x5 mean, median. You see blurring. The noise is reduced, the median is better, but the mean blurs the edges. Again, there could be some blurring in the projection. If you take the original PDF file and zoom in, you can see the details. So we did many of these We applied many of these filters and tried the LLMMSA filter, refined the updated recursive Wiener, adaptive neighborhood. This is our filter, and it's hard to compare. But you could compare, and we cannot compute any RMS error here because we don't have an original. We did some Fourier domain filtering. This is just to try all the filters we have studied so far, most of them. And you could look through them and come up with your own opinion as to which one does a good job and which one doesn't. So I'll stop the comparison here. In nuclear medicine imaging, I mentioned earlier about gated blood pool imaging. This is also a kind of multi-frame averaging. Depends on how you view it. So nuclear medicine images are typically acquired under low photon conditions because of the radioactive material that you inject into the patient. You have to be concerned. You have to take into account the bad effects of the radiation. For a number of hours after that, the patient will be still emitting gamma ray photons. It'll take some time for that to be passed out, to be excreted. Counting of photons emitted over long periods of time reduces the effect of noise and improves the quality, but then imaging over long periods may not be feasible due to motion artifacts. And also the patient won't sit there for 2 hours. So here is an example with that phantom I mentioned. The geometry of the phantom is shown here. This is just an image. So there is this drum, plexiglass, and 2 tubes that are filled. Actually, it's a solid cylinder with these holes drilled. So in the holes, you put the radioactive material. So there are 2 big holes and pairs of holes like this. 1, 2, 3, 4, 5, 6, 7, 8 of them actually. And these are, the dimensions are there in the book. I won't go through that. So if you acquire these, in this case, we can count the photons for a longer time. So the first one is 2 seconds, 15 seconds, 40 seconds of counting the photons. So the longer you count, the better the quality. In 2 seconds, there is nothing really. It's so noisy. Even here, you cannot see the very small ones. There's a lot of blurring. The resolution is poor. But compared to that, it's clean. Compared to that, it's clean. And this is gated blood pool imaging, where the ECG is taken. The patient is administered this radioactive material. There are 6 phases of the cardiac cycle here. The heart, the left ventricle. The left ventricle is contracting, the smallest here, and then it is expanding back. The size of the left ventricle and how much blood it is pumping out is of interest. How much blood is remaining after full compression and how much it is with relation to when it is filled. A certain amount should be ejected out at every compression. If it's not ejecting much of the blood, then there is a problem in compression. Now, how is this obtained? There's still some blur. The ECG is taken. The QRS complex corresponds to contraction of the ventricles. So this is systole, the beginning of systole. So you detect this using techniques, as in my other book. I'm promoting my other book, which is not here, but it's in the library. Paperback editions of that book have been published here. I don't know why they didn't do the 3rd edition yet. The 1st and 2nd editions were published by Wiley, India, in paperback. But anyway, detection of the QRS complex is not a big thing now. That was part of my PhD thesis project anyway. from 1976 to 1980, that was current research then. Now your smartwatch or something does it. It has become a consumer electronics thing. So you detect the QRS and then put a window there and say for those how many ever milliseconds, when the photons are emitted, I'll put them in this frame. That's an image. So all those photons, it's a 2D camera, the gamma camera or Anger camera. So it acquires the image and puts it there, and the next window of how many ever milliseconds, you can divide the cardiac cycle into 8 parts or 6 parts, not 50 parts. And then take that and put it here and the next and here and so on. And when the next beat comes, that QRS complex, that window data will go to the same phase as for that beat. So for every beat, when the QRS comes, the data will come to the same buffer. So if you take one such, you can say it is one frame. And when the next beat comes, you can call it another frame. So then you can call it multi-frame averaging. You don't have to divide. If you want, you can divide, it doesn't matter. It is accumulation of the counts. Is it multi-frame? A sort of multi-frame averaging. And these were averaged over 16 cardiac cycles. Each one of them was averaged over 16 cycles. I couldn't get one cycle data. They don't save it. So I cannot show you what it would be if you acquire only one cardiac beat. It was not available. But anyway, with averaging over 16 cardiac cycles, you can see the ventricle changing its size and shape. There is some accumulation in the thyroid and other parts. The rest of the body also takes up some activity, but not as much. It is tagged to go preferentially into the heart. Okay? You said 3 o'clock, right? Okay. Okay. Any questions about removal of artifacts? We have seen a number of filters.
I was observing like this. For example, what we process filtering everything for computer processing. It's not for, there is that helps the doctor to see and diagnose or whatever it is. But finally our computer processing is for computer understanding.
Okay.
Because computer can understand some pixel value, but human may not perceive that.
Yes, we don't consider pixel values. You don't sit and read each value. You look at the whole picture, and our visual system is good at doing that. These images I'm showing, I'm not showing any medical application yet of noise removal. What I've seen is noise is not a big issue in many medical images, including mammograms in particular. They said, okay, it looks nice and clean. I don't need any filtering. Noise removal always comes at the cost of some smoothing, and they don't like smoothing. They don't like edge blurring, especially. Radiologists are even happy with these images. These noisy 64 by 64 pixel images, they do diagnose with this. If you filter that and there is blurring, they don't like it. They're used to that. It's a question of, the point is they're trained with that. Okay? They're trained with that and they can detect it and they can do that very well. And if I go and say, I filter it, I look at this Wiener filter and all the fantastic things, they say, yeah, the noise is reduced, but you blurred the edge. And I don't want that. So even a little bit of blurring of the edge, they do not tolerate. So noise removal in all of our work has not been found to be suitable for medical image interpretation by the radiologist. It's a pre-processing step, both for computer analysis and for other steps after which you may give the image to the radiologist. So the next chapter is on image enhancement, and I'll show you assessment of mammograms with enhancement. We did detailed studies of enhancement, not noise removal. We concentrated on mammograms because I got research grants for that, and I had a collaborator, and we collaborated with the breast cancer screening program in Alberta, and nobody was interested in noise removal. They were interested in contrast enhancement. And we did, with many radiologists, we did detailed analysis, and we gave our program to others, and they did analysis of enhancement, contrast enhancement. Contrast is always the issue. But when you do contrast enhancement, you have to take care of noise. You don't want to enhance noise. You don't want to blur edges. So those are required. So controlling noise becomes part of contrast enhancement. This is also enhancement, but the focus is on removing noise, not sharpening. Next, we will see how to sharpen edges if that's what you want, or to enhance contrast if that's what you want, while controlling noise and while controlling unwanted blurring. But typically there won't be blurring there, there'll be enhancement of noise. When you enhance contrast or sharpen edges, noise also gets boosted. That's the price to pay there. Here, you want to suppress noise, you lose sharpness. Opposite. There have been other studies. I'm not saying it's not important. There have been other studies in the literature on removing noise in mammograms too and evaluating them. But you're right that some of these steps are for subsequent processing of the result using computers. Some of them are for subsequent processing by human experts. So depending upon what the next step is, you have to choose an appropriate method that suits that step. Okay? So I call this next chapter image enhancement, but to be specific, you could say edge and contrast enhancement, or improving the appearance of the image or appearance of some aspects of the image that are of interest. So in many practical applications, there are some issues that will limit your capability of getting a good picture. You cannot blast the patient with more and more X-ray photons, or inject more of the radionuclides, or take the picture over a longer period of time, or make the patient stay in the MR scanner for longer. There are limitations there, and you always sacrifice. Patient safety and well-being comes first. If you get a poorer image, then that's you have to deal with that. So what happens? You get less than the desired levels of contrast, visibility, of detail, or quality. What is quality? We said earlier, we need to characterize quality in terms of high frequency content, acutance, sharpness, contrast, and so on. We saw a few measures. So in several situations, the understanding of the exact cause of the loss of quality is limited or non-existent. You may not know what is causing this blurring or loss of quality. An attempt to improve the quality of the image using several techniques applied in an ad hoc manner, meaning I'll try this, I'll try that, if one works, fine. So then that is what is called image enhancement. You're not applying any optimization criterion here. It is not restoration. When you apply a specific model of degradation and have a specific optimization technique, like the Wiener filter for deblurring I showed, then that is called restoration, image restoration, with deblurring and denoising. When you don't have such criteria and you simply say, oh, I like 3x3 mean, median, this, that, try all of them. If any one of them or two of them work, then be happy. That is the ad hoc manner of image enhancement. Some of them do have models. It's not like they are totally how should I say, baseless. They have a basis. Some of them have a basis, but does that suit your application? That we don't know in some cases. So in some applications, I say a non-specific improvement of the general appearance of the image may suffice. Make the image sharper, let the details come up a little better, and the user is happy, fine. What are these situations? Microcalcifications in mammograms, lung nodules in chest X-ray images, the vascular structure of the brain. If there are very fine fractures in the ribs, it's hard to see them. If you can enhance them and make them visible, assist in the diagnosis and detection of them, then something is achieved. So some could be difficult to see due to small size, subtlety, small differences with respect to surrounding structures, low contrast, superposition by other tissues, as I said, breast tissues, normal tissues, and calcifications and tumors. They're all superimposed. Then the calcifications may not be visible. So what is desired is enhancement of contrast, edges, and detail visibility without causing any distortion or artifacts. So you don't want to cause something else to appear, leading to false diagnosis. So a basic enhancement technique is digital subtraction angiography. It's just A minus B. So just subtraction helps. But to achieve that, it's not easy. I was telling this to one of my PhD students I had worked with a medical imaging company. I said, well, why is a digital subtraction angiography system so expensive? You're taking one image, you're taking another image later, and you're subtracting. It's not like a CT machine where we have all these algorithms. He said, no, there are some complications involved, and it is not so simple. Okay. In DSA, or digital subtraction angiography, you take a picture of the patient first, and then you inject a X-ray contrast medium, an iodine compound, which is heavy substance, so more attenuation, and it fills the blood vessels, and the blood vessels will attenuate the X-rays more than before. And the change is only in the blood vessels. So you take a picture after, a little after the injection has been done, and the contrast agent has settled in the parts of the body that you are interested in. Take a picture and then subtract the two. So the difference is only in that injected contrast medium, so the blood vessels will show up. A number of images are taken. I don't know how many they take. A few, I shouldn't say a number, a few images are taken as the agent spreads through the arterial network and before it is dispersed and excreted out, so that will take more time. So within a few seconds, you do this. An image taken before the injection is used as a mask or reference, and you subtract that out from the live images where the contrast agent is coming through. So, being an engineer, I wanted to put an equation for everything. I don't give lectures without equations. And I was told, this is a plenary lecture, just talk. I said, no, I want to have at least one equation. So A minus B, F1 minus F2, if you want to write an equation. But there are artifacts due to movement. Even within the few seconds, the head you can put a clamp and hold it, but other parts of the body you'll be moving a little, and that causes some artifacts. And even within the head, even if you hold the head steady, the arteries are pulsating due to pulsating flow of blood, and that causes artifacts. You cannot hold that. And allergic reactions to the contrast agent. Some people develop allergic reactions, some may even die. There have been cases in Alberta. There are different types of these contrast agents, and the government, because healthcare in Alberta and Canada is funded by the government, funded by me, taxpayers. They are spending our money. But it is controlled by the government, by the health authority. They determine how much to spend on this and that. And there are different types of contrast agents available. Some are, some cause allergic reactions. They are known to cause allergic reactions to a larger population, and some have a lower level of that risk. And the government has to balance between the two. The healthcare authority has to. and there was a dispute as to which one they should use. So that is a risk. There is a cost-benefit analysis everywhere. So this is from one of my friends in the Netherlands. They gave this image. These are the two images before and after. So this is the brain. You can see the midline, the socket of the eye. You cannot see the vessels here. After injection, you can see the vessels here. So the difference is very small. It's not like it'll just pop up like the bone here. That, and see here, you don't see the blood vessels. You see a few here. You see some here, but those, I can't see them here. This is the subtraction, but there are many of these artifacts due to motion. And even the blood vessels, there is some motion here. They have a motion correction method, and this is after that, which is clearer. You don't see these artifacts here. This is from the Netherlands by Meyring and Zuiderveld and Veergever. There's an interesting dual energy and energy subtraction X-ray imaging technique that was developed in Chicago. The subtraction technique I showed just now, you have to take multiple images, one after another, at least two. That means more radiation exposure. In this technique, there's only one exposure, but they put filters in the cassette with the film or detector, and there are multiple films or multiple detectors with copper or aluminum filters in between. The filters will stop some of the soft X-rays. The X-rays have already passed through the body, but within the spectrum of the X-rays, there are low energy photons and high energy photons. High energy photons have already come through the body, and some low energy photons would have been absorbed right away at the skin. Those are not important. Others have been attenuated by passing through the soft tissues. They contain important information. But you want to separate that spectrum. And how they do that is by putting a copper plate in between the film. Suppose they're using film, 2 layers of film, 1 filter. And the filter will stop the soft part of that radiation that has already gone to the patient. The hard X-rays will go through. The hard X-rays would be related to denser parts like bone, soft due to soft tissues. So they get multiple images like this, at least 2, and then take a weighted combination of them. Depending upon the weights you apply, you can emphasize the soft tissue or the hard tissue. So X-ray measurements, now remember that different materials have varying energy-dependent X-ray attenuation coefficients. So the X-ray attenuation coefficient of this piece of tissue depends upon the energy of the beam, the photon energy. And the X-ray beam we get from the X-ray tube has a fairly wide spectrum. There is a filter there, but still it has a wide spectrum. X-ray measurements or images obtained at multiple energy levels, known as energy selective imaging, could be combined to derive information about specific materials, not elements. In some cases you could, but here soft tissue and hard tissue. There are some techniques where you can get information about the presence of certain elements. Weighted combinations of multiple energy images may be obtained, in this case, to separate soft tissue and hard tissue details. Typically, to do this, you get multiple images, but that has the disadvantage that the patient has to be exposed repeatedly at different energy levels, and that is the kilovoltage in the tube that is applied for the acceleration of the electrons. And then there will be motion artifacts. So in this technique, there are multiple plates separated by a copper filter. So they used plates that give you a distribution like a charge distribution. It's indirect digital radiography, that's what they used. The first plate gives you the full spectrum of what has come through the patient, plate or film. The copper filter passes only high energy photons of what is there. And the second plate takes a picture of that. Bones and calcium-containing structures would have preferentially absorbed the low-energy components of the X-rays. And high-energy components would have passed through low-density tissues without much attenuation. So the second plate has information related to dense tissues and bone. So the two plates capture two different views from the same X-ray beam, one exposure. The patient is not subjected to two or multiple exposures. There is no need to worry about motion artifacts. Weighted subtraction of the two images provides various results. I asked for some details and he said he couldn't give me that because it was licensed to a company. And I couldn't get the separate images. So this is the full spectrum, what is called CR, computed radiography. That's a confusing name. What it means, it's a charge plate like in your photocopier, and that is exposed to X-rays. There is a charge distribution that is scanned, and you get a picture. It's not computed, it is scanned. Whereas direct digital means it's a solid state digital detector directly without converting the X-rays to light or to some charge or some other form of energy. So CR and DR are the terms used. Computed radiography, when you have a charge plate and that is scanned later to get the latent image out. Digital radiography or DR, when you have a direct digital solid state detector directly for X-rays. So Dr. McMahon at the University of Chicago developed this, and this is the full spectrum chest image. So you see all the details, bones and ribs and some lung structure and the heart and diaphragm and all that. So this is the bone detail image, and this is the soft tissue detail image by energy subtraction of the two images obtained simultaneously. I asked for details about the weights and the two images separately so I could try different operations, and he said he couldn't do that. It was licensed to some other company. So from the two images, you get the separation of the hard tissue and soft tissue details. And there is a small dark spot here that shows better here than there. That's the normal, typical image. And here you have two separate images obtained by manipulation of the two images obtained in one shot. So that is subtraction, just A minus B. But you can also do that over time. But for change over time, temporal subtraction, time-lapse subtraction of images or scenes, when something is moving and changing, you take one at this instant, another later, and subtract, and you get what changed in between. It could also be a patient's image from today and next year, or this year and last year. But then that's not so easy. It can't be A minus B. You have to register. I would have changed I was joking with my sister-in-law. I was telling my size was 42 before I came, and one day after I came, I went shopping, my size was 44. I said, I'm eating too much here in India. So we change, especially over a year we change. And you can't simply subtract the two images, you have to register. Hopefully there are some marks, some landmarks. I'll talk about landmarks later on the last day or the last 2 days. You take those landmarks and register the image, and you also have to do some geometric mapping, and then you can subtract. Otherwise, pixel by pixel subtraction doesn't work. So time-lapse subtraction of images is useful in detecting normal or pathological changes that have occurred over that period of time. Radiologists do this. Mammograms taken in a screening program. When a woman goes for this imaging today, the previous images from the last year or the previous screening, typically 2 years ago, and the one before that, 4 years ago, they're all brought up and they compare. They don't do subtraction, they just compare. Visually, they do the subtraction, mentally. So normal anatomical structures are suppressed and pathological changes are enhanced. That's what you would want. Registration is crucial in temporal subtraction. Otherwise, you get artifacts. You saw in the digital subtraction angiography, even within a few seconds, the pulsatile movement of the vessels will cause artifacts. Geometric transformation techniques are useful in matching landmark features, but you need landmarks for registration. So you require detection of those landmarks. That itself is a big issue. So those are some other topics to consider. So let's look at transforms for enhancement now. Different types of enhancement and different types of transforms, not the Fourier transform, but grayscale transforms. How do you change the grayscale values in an image? Grayscale thresholding is simple. Convert a grayscale image with a range 0 to 255 to a binary image. So I put a threshold and say everything below this is not of interest, everything above that is of interest, but just give it one value. I don't care about the variations in the two ranges. So GMN is 0 if FMN is less than or equal to L1, and 255 if FMN is greater than L1. So L1 is some threshold. You have to determine the threshold in an optimal way. It's a bi-level or binary image. This is bi-level, this is not 1. If it is 1, you call it binary. So essentially you're saying pixels less than L1 are noise or background that I'm not interested in, and gray levels of objects of interest are greater than L1. You can also say if it is less than L1, I'll make it 0, but if it is greater than L1, I'll keep the original value. So the variations are retained. So here is an example, a CT image of the patient I showed earlier with neuroblastoma, the tumor. Here, B is, okay, this shows the Hounsfield unit range of minus 200 to plus 400. Anything less than minus 200 is black. Anything more than 400 is saturated to 255. This is thresholded at 200 Hounsfield units. So the calcified tissues, the bones, the spine, spinal column, and that the examination bench of the CT scanner, they are visible. So you have these bits of calcification within the tumor. Here, values above the threshold are retained in their original value, about 200. So this shows the difference in density between this and that. The calcifications are not of the same density or Hounsfield units as the ribs. Here, they all appear the same. And in D, the Hounsfield unit range of 0 to 400 has been mapped to the range 0 to 255, whereas here it is from minus 200 to plus 400. From 0 to minus 200, you have fat. Water is 0, fat is minus 10, 20, and air is minus 300, 400, minus 1000 would all be air. So if you're not interested in anything less dense than water with negative Hounsfield units, then you may use this 0 to 400. This is a pediatric case. Above 400, there may not be many pixels. 400 is fairly high density bone. Adults will have high density bone, but not a child. So you may say this is enough. And then the details within are seen a little better. You select that, window that, and then look at the details. This is not bad, this is bright, but this is in a limited range. So these are thresholding, these are just rescaling. This is necessary, this windowing is necessary with CT images because CT images will have a range of plus minus 1000 and you can't display the whole thing. If you do, then you'll be compressing all the details. You will not be able to differentiate between soft tissues of various types. So that is called grayscale windowing, which was already done there. In grayscale windowing, you say, well, my image has such a big range, I can only look at small parts. The human visual system can only discriminate between some 30, 40 gray levels. If you have 0 to 255, you say there are 256 gray levels, but it'll be hard for a human observer to separate all of them. More so when you have a CT image with minus 1000 to plus 1000, 2000 values. Can you, in an image that has a range of 2000, would you be able to separate two things that are differing by 1 or 2 Hounsfield units? Quite likely no. If there is a difference of 10 Hounsfield units, maybe you will see. But if you take a small window of the grayscale and expand it, then you can see the difference. So here you say GMN is 0 if FMN is less than F1, some limit. It could be minus 1000. FMN minus F1 divided by F2 minus F1. That's a scaling factor. The range of interest is defined as F1 to F2. That's the range I want. Below F1, make it 0. Above F2, make it 1 or 255. Multiply this by 255, you get, and make them integers, you get 0 to 255. Otherwise, 0 to 1. Later on, that multiplication factor could be something else. If you are doing computer analysis, you may make it 1000 or whatever you want it to be, but for display 8 bits, 255. So greater than F2, 1. So in details of interest in the range F1 to F2 are stretched. So it could be small, just from 0 to 100 Hounsfield units. Stretch it 0 to 255, so you're doubling the differences in the range. So you can see the abdominal organs which are in that range, 50, 60, 70, 80 Hounsfield units. If you keep 0, water as reference, that will be good. So this is linear. So GMA is the windowed image with the grayscale normalized to 0 to 1. F1 to F2 is a range selected for display. Pixels below F1 will be eliminated mid-black. Above F2 will be saturated and shown as white. Details within the range F1 to F2 will be displayed with increased contrast, but it depends. What is that range? If your display range is 0 to 255, if you choose minus 500 to plus 500, a range of 1000, then you are compressing. If you choose a small range like 0 to 50 or 0 to 80, and then expand to 0 to 255, you are getting better contrast. So it's up to you as to what you want to do. If you want to see fracture, then you choose maybe 200 to 1000 and let all the soft tissue go away and take only the bone and take 200 to 1000 and map to 0 to 255. You can see fractures better. So this is just linear stretching. So this is the original image. 0 to 0.6 has been taken, mapped to 0 to 1. And 0.2 to 0.7 mapped to 0 to 1. So if I put a threshold of 0.2, some of the low density details have been removed. If I'm going only to 0.6, so some of the high density details are saturated here, but they are retained there. So it depends on what you want to see. The range is, I'm using normalized range, 0 to 1. This is the histogram of the original image going 0 to 255. So you can take some part that you are of interest. So the transformation, one of them is that, and the other is this, linear. One saturates there, the other saturates here. And there is clipping here. The two transformations I described now. Graphical representation. This is the myocyte image. This is what I got originally. And I stretched that 0.2 to 0.6 to 0 to 1. So I can see the details better. There is some improvement of the visibility. Just because this is a very dark image, it's been brightened. And some parts have been saturated here, white. There is no contrast enhancement. It's only stretching. That gives you increased visible contrast, but that is achieved only by stretching the values and selecting a small range to display. Okay, past 3 o'clock. 5 minutes past. Okay, let's stop here and we'll have a tea break. Of a myocyte, the original image was a bit dark. So just by linear stretching 0.2 to 0.6 to 0 to 1. So this is on a normalized scale of 0 to 1. You can achieve some enhancement of the contrast and brightness, but if you look at the histogram, this is the original histogram, and after stretching, you have many unoccupied levels in the histogram. So you're not still making full use of the information available in the sense the histogram is limited to this range. There is a little bit of stretching here, but many levels are unoccupied. So that's not the best enhancement, but it is a poor image to begin with. These are linear transforms, except for the first one, thresholding, that is nonlinear. Stretching, like I have shown, is linear. There could be clipping at the ends, but within the transform portion shown, it is linear. I showed this HD curve earlier for an imaging system. It can also be used for enhancement. This is a curve that shows in a certain range I want to cut values, and below this value I want everything to be 0. And above that value, some value, I can saturate, I don't care. In between, I want good enhancement, stretching, like this, or more stretching. So this is known as gamma of the imaging system. That's the response of the system. If you know that for the system you acquired, from which you acquired the image, you can correct for that. If you want a linear response, you are going to invert it. But if you are using this idea for enhancement, you are not concerned with what happened during image acquisition, the gamma of the image acquisition system, but you're simply saying, I'm going to use a nonlinear transformation with this gamma function. A system with a large gamma has image with high contrast, as I mentioned earlier. It may not utilize the full range of the available gray scale. Small gamma, image with wide latitude but poor contrast, wide dynamic range. Gamma correction is a nonlinear transformation that says GMN, the output is FMN times gamma, FMN to the power of gamma. Now for this, the grayscale is normalized to the range 0 to 1. Divide by the maximum and then apply this. There is another definition where you can take the log of FMN, you're not normalizing, it could be 0 to 255 if you wish, divide by gamma, and that's also gamma correction. You can also incorporate grayscale windowing and say below some level I don't want, let the output be 0, above some level let it be maximum, and in between apply gamma and nonlinear transformation. So here we have a chest X-ray image, gamma equal to 0.3, gamma equal to 2.0. So different details are enhanced. Soft tissue details come out better. Hard tissue details are saturated. Hard tissue details are there, and soft tissue Here it is enhanced a bit, but this part is lost. So it is selective enhancement. So by getting multiple images of this nature, you concentrate on certain regions and design suitable enhancement parameters for those regions. If you want to examine the other regions, you apply another gamma value, get a different output image. So if you don't do any transformation, linear is that is gamma equal to 0.3. So there is enhancement here, but after that there is not much enhancement. Here there is more enhancement on the lower side. What is 0 to 0.3? Sorry, it is compressed here. 0 to 0.3 is compressed to 0 to 0.1. So some parts are compressed, some parts are enhanced, stretched, depending on the value of gamma being greater than 1 or less than 1. Now, histogram-based techniques were popular. There are some limitations, but there are some interesting aspects. So we'll quickly go through a few histogram-based techniques. The image histogram is normalized and interpreted as a PDF, as a probability density function. You only have one image, so you take its histogram, divide by the total number of pixels, and call that a PDF. So based upon information theory, the information conveyed by the image is maximal when the PDF is uniform. But we are taking the PDF of one image, so it's only approximate. And the idea of a flat histogram conveying maximal information is based on information theory using probabilities that may not always apply to real-life images. So there are limitations. The entropy of the PDF is maximum when it is uniform. So the technique of histogram equalization is proposed as a method to enhance the appearance of an image based upon these principles. Will that work? We will see. So you have an image FMN and you have the histogram PFL. Divide by the number of pixels and let PFR be the normalized histogram. Let R be 1 over L minus 1, so that the grayscale is in the range 0 to 1. You're normalizing the counts of the pixels as well as the pixel values. Then you have a probability density function PFR. F is the input image, R is the input variable. And if you apply some transformation, S equal to TR, then the output is given by PGS. G is the output image, P is the probability density function, S is the output variable. The input PFR times the derivative of dr over ds at R equal to T inverse S. Then the resulting image GMN will have normalized gray levels in the range 0 to S. S being between 0 and 1. The input is also in that range. So S equal to TR, and you want to design it so that the output histogram is flat. So the derivation of this is in the book by Papoulis that we use as a textbook for random variables. It's also in the book by Gonzalez and Wentz. The transformation you want is integral of the PDF of the input image. W is some temporary variable, integrated. So if you integrate the probability density function, you get the cumulative distribution function. Some call it probability distribution function. So this TR now has these important properties. It is single valued and it is monotonically increasing because you are adding probability values that cannot be negative in the interval 0 to 1 for R. This is necessary to maintain black to white transition. When you apply a transform like this, you cannot go backward and reduce the output gray level when the input is increasing. So you want monotonically increasing functions for the transform. And this transform output is between 0 and 1 for the input being between 0 and 1. It maintains the same range of the variable R and S, input and output variables. Now the derivative of this transformation is PFR. The derivative of the integral is just that function. So we said earlier PGS is PFR times its derivative of the transform, and that is 1 over this, so it is equal to 1. So regardless of what the input PDF is, the output PDF is 1 due to this transformation. So all you do is integrate or apply a cumulative summation procedure to the input histogram, and that itself is a transformation. And because they're all normalized, the values are all between 0 and 1 for the variable and also the probability. So TR equalizes the histogram of the given image. The histogram or the PDF of the output image is flat or uniform, and that has maximal entropy. The histogram has maximal entropy. Will the image have maximum quality? That varies. In the case of a discrete image with discrete gray levels, then there are a few issues. Implementation in practice. The derivation was with continuous variables. Now when you have discrete variables, you have an image fmn, p equal to mn pixels and L gray levels, so they are quantized. Divide by the maximum, so Rk, the quantized pixel values are between 0 and 1, but then there are only L of them, L values, each occurring nk times. So the PDF may be approximated by the histogram nk over p. Number of times each pixel occurs divided by the total number of pixels, that's all. The integration sk equal to trk, the transformation, is sum I going 0 to k pfri. The integral becomes a sum of all the probabilities of occurrence of the input gray levels, which is sum I going 0 to k of ni over p. Ni is the number of times the ith gray level occurs in the input. Discrete. So this is the transformation. Output is sk, sum of these values which are all between 0 and 1. And that sum could be something different from these Rk quantized levels, which are 0, 1 over 255, 2 over 255, and so on. And these values are something else. So you need to map these values back to one of those input levels. That is where some approximation comes in. Take the nearest available level, and then there are some undesired effects. Discrete histogram transformation may yield values of sk, will yield values of sk that may not equal the available quantized values for display. You have to multiply that by 255. The values will have to be re-quantized, and hence the output image may only have an approximately uniform image, but in a uniform histogram, but it is not. Typically, it is far from that. So the resulting values in the range 0 to 1, you scale to 0 to 255 for display. That's not a problem. Regardless, the quantized levels are remapped, and many of those values of sk may go to the same output value. So histogram equalization is typically implemented as a lookup table. LUT is lookup table, sk-rk pairs. You prepare that and apply as a lookup table. As long as the PDF is the same, you use the same. So if you have a population of images with an averaged histogram taken and an average PDF, then that's fine. You're not computing the PDF from one image. Then the same lookup table could be applied for that whole category of images. So the problem is this: a quantized histogram equalizing transformation may contain several many to one gray level mappings. Many input levels will go to the same output level. So it is not reversible. Reversing is not important, but many of them going to the same value will cause some artifacts. So the transformation is non-unique and irreversible, but that is not the main issue. Sometimes it works. So this is a girl in a snow cave. One of the daughters of my grad student, William Morrow. So she is sitting inside the snow cave. Even kids play in snow. It could be minus 30, but even if it is minus 30, kids have to go out and play in outside when there is a recess in the school. And they have camps where they go in the winter, and they build snow caves, and you can build an igloo. Not you, I wouldn't do that, but my son has done that. In scout camps, they go and they build an igloo, and they have to make sure it is strong enough, stamp it and make a hole, and they sleep and spend the night there. I don't know why they do that, but they do. So then you want to take a picture. There is a lot of white snow on the outside reflecting light, and she's inside and there's not much light there. Your camera takes the average light intensity, and that's the original picture. It's a, yeah, and this is histogram equalization. Not bad, you can see her, but it's a little blurry. That's not a problem, but better than that, right? In terms of visibility of what is inside. And this is linear mapping, 0 to 23 mapped to 0 to 255. I took only this range, and that disturbs me. Excuse me, I can't. Thank you. But everything outside is saturated. So if you want only that part of the image, you can do a linear transformation, or you can do a gamma correction, 0.3 gamma. So this is not bad. There are variations there, which you can see. There are variations inside that are retained. Is this better or that? It's up to you. There are no rules here as to say which is better. Look at the histogram. This is the histogram of the original image, and this is the histogram after 411B's histogram equalization. Not bad. The histogram has been spread. It's not equal, but flatter than that. You want a flat histogram? Is this flat? No. Is this flat? A little bit. But many levels are not occupied. 0 probability. Clearly, this is a multimodal histogram. That is the histogram equalizing transformation, or the lookup table. There are these steps. So all of these input levels will map to that output level. So many levels don't exist in the output, which is why you see these holes or gaps. So the X-ray image and chest X-ray and histogram equalization. The lookup, the transformation is sort of almost linear. There is not much gain in here. There is not much improvement, and this looks almost like a straight line. That's the histogram of the output. The original histogram, I think we saw somewhere else. In 4.6 somewhere, we don't need to go back. Here it completely ruined the image. This is that myocyte image. Histogram equalization has enhanced all these details which we're not interested in. The histogram equalization almost looks like a step function. There was a big spike and then the histogram went low. So suddenly the values increased when integrated, and then flat, and here flat. So all of these have been either saturated or clipped. That's the output histogram. It's not uniform. It's not just the histogram being uniform. There are other structural details and structural information one needs to look into to judge whether the result is good or not. In textbooks, there is another method called histogram specification, where you can say, well, the uniform histogram may not always help, may not give a good image. I'll specify what the histogram should be for the output. How I'll do that, that's a different question. How do I know what kind of histogram will lead to a better image? If you have some information about that, then you could draw or specify that histogram, and then say, let the output have that kind of a histogram. For that, you have to put in series two histogram equalizing procedures. Histogram equalization can only give one output image. Take it or leave it, as we saw. In many cases, you will leave it. The user has no control over the procedure or the result. So if you want to have a choice, then you say, I will specify the output histogram. And we have a series of histogram equalization steps that will give you an output that is close to the pre-specified histogram. May not be exactly the same. And if you can specify several histograms, how you do that, again, I don't know. Somehow you do that with some experience, and you can get several enhanced images, and then you can choose one of them. So suppose PDT is the desired, D is desired, T is the variable for that histogram, is what you specify. The input image F has PFR as its PDF. We earlier saw S equal to T1R, integral of PF, will give you histogram equalization. So this is one step of histogram equalization from the input end. So this gives you a flat histogram, theoretically. Now you do another histogram equalization from the other end. To do histogram equalization, you only need the PDF, PD. You don't need the image. The transformation is computed by integrating the PDF or the histogram. You can draw a histogram without having an image. So integrate that and have this Q equal to T2T as an equalizing transform applied to your desired histogram for which you don't have an image. Now both of these will give you a flat histogram. Then you'll say, well, that histogram is the same, it's a flat histogram. Let me connect the other two histograms through one transformation. So let the hypothetical image so obtained be E with gray levels Q, and T equal to T2 inverse Q will map the gray levels Q back to T. Now this PGS and PEQ are both uniform PDFs and they're identical. So the desired PDF may be obtained by applying T2 inverse to S. You have two transforms, T1R and T2, but now T2 inverse applied to S. We assume that T2 inverse exists, and that is a problem if there are many to one transformations, if there are those steps in between, and they exist. It is not a single valued or unique transform, but we will assume that is possible or approximate. So in practice, you cannot do the inverse, but you match the two lookup tables and try to put them together. There's one lookup table for the forward equalization transform from the given image. There is one lookup for the reverse histogram equalization from the desired histogram, and make lookup tables for the two and somehow connect those values and make one transformation from input to output. So specify the desired histogram PDT. Derive the histogram equalization transform Q equal to T2T. Derive the histogram equalizing transform S equal to T1R from the input image PFR. Apply the inverse transform T2 to the PDF obtained in that step. T equal to T2 inverse S, and then T equal to T2 inverse T1R. Combine T2 inverse and T1 apply to the input gray level R, and that is the full specification transform. Apply that to the input image F, and that gives the desired result D with the specified or an approximation to the specified histogram. Many of my students did projects on this and implemented various algorithms with interface and so on, but we never got any result worth displaying. You can draw whatever histogram you want, and I don't have any result to show. Textbooks, Gonzalez and Woods may have some, but I didn't find any particular advantage any further than equalization. It is something fun to try perhaps, but it hasn't led to any great applications. But theoretically, there is some interesting procedure here.
But one probability distribution to another distribution, desired distribution.
Yeah. And it works in the continuous case with the assumption that these are, at least one of them is reversible or invertible. But in a practical case with quantized gray levels and many-to-one transforms in both T1 and T2, there are approximations. And you further approximate by making one lookup table. So if you want, you can try, but there is nothing great about it. I still keep it as an interesting topic. You may take some of these ideas and put them elsewhere. Now, these are global operations, the histogram operations. So they don't take into account the non-stationary nature of images, one histogram or PDF for the whole image, like one spectrum for the whole image. So you want to have local and adaptive transforms for effective enhancement. That leads to what is called local area histogram equalization. This has been popular more than specification of histograms. There are many variants of this LAHE, L-A-H-E, local area histogram equalization, contrast limited, CLAHE, and various AHE, and so on. So Ketchum came up with this procedure and said the histogram of the pixels within a 2D sliding rectangular window. So for the pixel being processed, you put a window and compute the histogram there and equalize that and apply the result only there for that one pixel, move and keep repeating. That's expensive. So the result is applied to only one pixel. It's repeated for every pixel. The window provides a local context. That's fine, it is adaptive. So Peiser came up with many variations of this. The histogram equalizing transforms are computed not for every pixel, but there is some interpolation. I'll divide the image into some blocks. I'll compute only a few histograms. And for other pixels in between, you interpolate between those histograms or those outputs. So some approximation to reduce computation. So it is not computed for every pixel, but only for a number of non-overlapping or in some cases overlapping blocks. And for other pixels for which you don't have the transform, you use the neighboring transforms, take their average and put the value there. The pixels at the center of each block are processed using the corresponding transform. Other pixels get interpolated versions of the transform corresponding to the 4 neighbors, which have the transforms. And then they applied some limits on contrast enhancement, said, within a small window, you don't want to stretch to the full range of the image. Then white becomes black, black becomes white, and so on. You don't want that. Within a small window, here, if you stretch to the maximum 0 to 255, that will become black, this will become full white 255. You don't want that. So you want to have the local range and limit your stretching to that range as you move the window. So here are a few versions. So this is the girl in the snow cave. This is global histogram equalization I showed earlier. This is locally adaptive histogram with 11 by 11 window, a 101 by 101 window. And these are not very good because there was no limit on the contrast. We didn't implement the contrast limited version of this. That would have given better results. We have that in the new book. We are working on it. We have some better results with contrast limited adaptive histogram equalization. We were more interested at that time with our version of the adaptive neighborhood. So we said we will use the adaptive neighborhood computed for each pixel, take the neighborhood, the ribbon also into account, take that histogram, do the equalization, apply that result to the pixel at the seed pixel and also the redundant seed pixels. So we got these two with different parameters, growth tolerance 16, background 5 pixels, growth tolerance 64, and background width 8 pixels, where if you use a large window, growth tolerance being 64, you get larger windows. This reversal is not good. Snow is not black. So that relatively dark region of snow has become black. You don't want that. It's a little better here. But a funny thing happens here with the enhancement of this edge of the cave. It looks like she has been pulled to the front. depth information is lost. There you know she is at the back. Here it, maybe, but looks like she has come to the front. So you lose some depth information when some cues are lost. The 3D perception cues are lost in this process. But you can see some details. There is that string here, which you cannot see there, but could see there, but you can clearly see here. The patterns on the boots are hard to see there. So there is enhancement. If you look at minor details. So in adaptive neighborhood histogram equalization, we use these adaptive neighborhoods. I think I can skip the details. I already said that. So here is another example, a test image. There is a box here. Inside that there is another box, and there is another box inside. Same here. If you do global histogram equalization, you can see one box there, which you cannot see here. This box, maybe you can see, you cannot see here, but there's one more inside you cannot see. That becomes a bit more visible here. If you drag the window, adaptive histogram equalization window, then the artifacts of the window will come. With our adaptive neighborhood, you don't see such artifacts. And if you were to adjust the lighting conditions and concentrate, you will be able to see another little square inside, which is not visible there. So test images like this will help in analyzing what can be achieved and what kind of artifacts could possibly arise. And we can make this to be just about the just noticeable difference and see what happens, and adjust the contrast enhancement parameters so that details that are at a certain level above noise are enhanced and those at the noise level are not enhanced. It depends on what you want to do. You don't want to enhance noise. There are a number of 3x3 convolution mask operators. We have already seen the 3x3 mean filter, we saw the Laplacian. But there are a number of other 3x3 convolutions that are popular through textbooks and in practical applications. They have been proposed for various types of image enhancement and edge extraction. An old technique that is popular, that was popular and is perhaps still popular, is unsharp masking. It's an awkward name. When an image is blurred by some unknown phenomenon, you could assume that each pixel in the original image somehow spread and gave its part of its value to its neighbors, like diffusing. You don't have an exact equation for diffusion, it is some spreading. So it spread, it had some value, it lost some value here and gave some value to the neighbors. So this, and it is additive. These values were added to the neighbors. A certain fraction of its value went away. Then each pixel is composed of its own value and fractional components of its immediate neighbors. The spreading of the value of a pixel into its neighbors may be viewed as local fog or blurred background. You could also model it as diffusion, but that's an entirely different procedure, and we are putting that in our second edition. I don't have it here. Diffusion-based image processing is another technique. There was a photographic technique that was popular when film was used and paper printing or printing on film was used. So in the photographic lab, what was done was if you had a blurry image, then the given degraded image in its negative form was further blurred to create what would have been the background fog. And a positive transparency is created. You make that, invert that and make it positive on film. And the original negative and the positive created after blurring are put together and then you make a print. But you must register them properly. If the edges are registered, then it's okay. The procedure leads to subtraction because one is positive, the other is negative. This blurred fog is subtracted out. So what the pixel gained from its neighbors in the process of image acquisition is now removed. So that was called unsharp masking. And a convolution mask to do that is this, which says from this value I'm subtracting an average of its 8 neighbors. But if I say 1 in the middle and minus 1/8 all the way around, the net is 0 and it's a differentiation. But I want to retain the intensity, so you make this 2. But you can change this if you want and adjust the weighting between retention of the original value and the derivative. If I make this 1, it is like a derivative, like a Laplacian. My central value minus the average of the neighbors. It's a local derivative. Plus 1, the current pixel. So the original image plus its derivative of some kind is what is happening here. So it's a convolution mask. You apply it on a pixel by pixel basis. There is no need to reverse. It's symmetric. The net sum of these coefficients is 1, so the intensity is maintained, average intensity. You can also write it in this format as we have seen in some of the filtering techniques. There is a combination between the input signal, GMN, and a high-pass version, GMN minus mu G. Signal minus mean is like a high-pass filter, plus alpha. Previously we had the mean here, with alpha being some ratio of standard deviations or variances. So here it is the original image. Original image plus its derivative with some controlling factor. If you make alpha equal to 1, you get that 3/3 mask. So there is a local gradient. This is a local gradient or derivative. So that is related to edges. And adding that edge information will give you edge enhancement. But this creates edge enhancement. It leads to high frequency and emphasis, but edges are enhanced. Do you want edges highlighted or not? Radiologists don't like edge enhancement. It's like highlighting. Strong edges will have clearly perceptible overshoot and undershoot. That's a problem. You have forward derivatives and backward derivatives, and that causes some artifacts. I'll show that later on. It could lead to negative pixel values in the enhanced image because there is a derivative taken. You're adding that with a weight factor, but still there could be negative values. What do you want to do with that? Do you want to set them to 0, or do you take the minimum to maximum and map to 0 to 255? It's up to you as to how you want to display the result. So here is that clock image. It's noisy by itself and unsharp masking. A little sharper. Some of these details are a little sharper. A little more noisy perhaps. We'll come to this later on. So this myocyte, there is not much enhancement, a little bit enhancement. This one, perhaps there is good enhancement here. We'll come back to this later. The knee, there is not much of an enhancement. This is already fairly good. Now this is one of our shapes image. It already has sharp edges, but I still wanted to apply this method and show the artifact that comes. You see a black line around the edges. This is the original object. This is after enhancement. The edge white, black. You don't see it everywhere. These are not very strong edges, but at strong edges you see that more obviously. You can see that there too. You may not be able to catch that on this full image with so many details, but it is there. The subtracting Laplacian is something similar, but it has some basis. There is a diffusion basis based on this partial differential equation. So it says the observed image G is a function of time. There's an image, the original image was there, and over time it is diffused, the intensity is somehow diffusing, it is spreading over space. Like you put ink on a blotting paper. I said blotting paper, and many of my students didn't know what blotting paper is or was. All of you know what blotting paper is? Tissue paper. No, not tissue paper. No, some of them don't know what, it's ancient technology. Blotting paper is thick, loose cellulose paper on which if you put liquid, if you put ink, it spreads. It was used to absorb ink. In olden days when you used ink pen or fountain pen, if you were to write, it would take time for the ink to dry, so you would use a roller with paper that could absorb that excess ink. It was called blotting paper. You would take the excess out. That paper absorbs the liquid, like your paper towel that absorbs water and so on. So that was called blotting paper, and nobody uses that apparently nowadays. But if you were to try to write something on blotting paper, you write something, it keeps spreading because the paper absorbs and it keeps diffusing. So if you were to put a picture on such a medium, it keeps spreading. And that is blurring. You draw a straight line, but it spreads. So like that, the image is changing over time, but spreading and getting blurrier due to diffusion. It could be heat that spreads if there is some conductive substance. It could be liquid that is spreading. It could be what else that spreads. Imagine some situations. And that spreading process is indicated as the derivative of the function g, the image over time, is kappa nabla square g, where the nabla square is the Laplacian. It's a spatial derivative. The temporal derivative is equal to the spatial derivative with a scale factor. That's the model for a partial differential equation for diffusion. It's a linear process here. There are some other nonlinear models. So at t equal to 0, we assume that gxy 0, this is time 0, is fxy, the original image. We don't have that. We took the picture sometime later. It's become blurry. So at t equal to tau greater than 0, the degraded image gxy tau is observed. And if you were to expand that in Taylor series, gxy tau is gxy 0 plus tau partial derivative xy tau, tau square over 2, second partial derivative xy tau, and so on. Ignore the rest, use only these. Then this is f. So you take the original is this minus that. But this derivative is nabla square, the Laplacian. This is also thrown out. So the enhanced image is g minus k tau nabla square g, the Laplacian. So from the given image, you subtract a fraction or some weighted factor of the Laplacian of the image. The enhanced image is a weighted subtraction of the given image and its gradient, which is the Laplacian in this case, according to this model. So there is a model. The unsharp masking also had a conceptual model, but no mathematical model. Here we have a mathematical model, and that leads to the Laplacian we saw is this in discrete notation. This is the Laplacian, the gradient. The sum of these coefficients is 0. Subtracting Laplacian, 1 minus that. So 1 minus 4 becomes 5, and around 1 you have 0, so these become minus 1. So that's the subtracting Laplacian. 5 minus 1 for the 4 connected neighbors. The 8 connected neighbors, the corners are not used. It's similar to unsharp masking. This minus the average of its neighbors. If you want, you can divide by 5 or 4, and if you divide by 4, you get the average of that, and this is 5 over 4, which is 1 plus 1 over 4. So you can see it in different ways. The other one was 2 and minus 1 over 8. The sum of this is 1. So there is a similarity. Unsharp masking is sometimes called generalized Laplacian. And this is also a kind of unsharp masking. The Laplacian doesn't maintain intensity information. It shows only edges or gradient. Subtracting Laplacian maintains intensity and provides a sharper image, enhancement. It again leads to negative pixels. You have to deal with that. But what happens with negative values is the input was 0 to 255. The output could be minus 200 to plus 400 or something. So the larger dynamic range. Now you have to display it to 0 to 255 for the output. So you compress that. So the enhancement you gained is lost by compression if you keep the negative values. So there are some practical issues and difficulties as to how to handle this. If you just chop off all the negative values, many parts will be set to 0, and that doesn't work. So mapping of this to the output is an issue. It also introduces disturbing overshoot and undershoot, like we saw earlier, and that can be visualized by this 1D signal. This is a rectangle pulse. Derivative will have those delta functions ideally, but here I'm showing like that. And when you take the second derivative, you get that. When you subtract the 2, you get this. So undershoot, overshoot, overshoot, undershoot. That is what is showing in the image as those black and white, brighter and darker lines. So this illustrates what is happening. Even if this edge is, of course, the edge won't be like that, it will be smooth. The derivative of that could be a Gaussian. And the derivative of that will certainly have positive and negative values, and that will lead to this problem. So this is the Laplacian, subtracting Laplacian. Because you're using the second derivative, noise is emphasized. In general, the subtracting Laplacian gives you more noisy image. It is sharp. 6, look at the 6 or 5. You can see the 5 clearly, better than those. But a lot of noise that's present in the image, it's been enhanced. The gradient shows the noise too. Laplacian, subtracting Laplacian. This is not bad. Better than that. I will just click through these and you may decide. Some of these, I don't know what they are. They look better than in the original. And the ringing artifact is clear. The gradient shows that. So fixed operators have certain limitations. Fixed meaning not varying over space. Subtracting Laplacian and unsharp masking, mean, median, they do the same thing all over the image. The coefficients and size of such filters don't vary. The filters cannot adapt to changes in the nature of the image from one location to another. So operators with fixed coefficients and fixed spatial scope cannot take non-stationarity and multi-scale features into account. Multi-scale meaning small objects and big objects. As in my test patterns, and even in the clock image, there is a big minute arm, a small hour arm, and then all these numerals. So there are objects of different, details of different scale. Multi-scale features cannot be taken into account because the mask is of the same size. The same thing is done all over. So we need adaptive filters. You said 4:30, right, today? Close early? Let me see where I am. Just a moment. Where am I? Okay, not far from the end, but I won't go to the end. High frequency emphasis is a frequency domain technique where you want to emphasize the high frequency components that are related to edges and sharpness. So you boost high frequency, control the low frequency. You can't remove them completely. You cannot remove DC, you need the brightness, but you boost certain components. High frequency components in the Fourier transform could be boosted. And it follows from the effect of differentiation we saw. When you differentiate an image, there is increasing gain for high frequency components. So the ideal high pass filter, like the low pass we saw, says HUV is 1 if DUV is greater than D naught, some cutoff, 0 otherwise. So this is a high pass filter. Everything below that cutoff is set to 0. DUV is square root of U square plus V square, distance from the origin or radial frequency. That simply extracts edges. The magnitude transfer function is this 0 inside this disk or circle, 1 outside. That is the Butterworth. Well, there's a smooth transition. So ideal goes 0 to 1. Butterworth goes slowly. If you take the Butterworth and apply a bias and raise the DC gain so it is not 0 but goes to here 0.5 and above, then it's a high frequency emphasis filter retaining the low frequency. More gain for high frequency than for low frequency. So the Butterworth high pass filter says similar to the low pass, just this is reversed, this ratio, D naught over DUV. For low pass it was DUV over D naught. That's all. So this is a monotonic function in the pass band and stop band, like what you see here. Monotonically increasing. Positive frequency, negative frequency in one section, radial section. N is the order of the filter. If you increase it, it will be a sharper transition. If the DC gain is 0, then intensity information is removed. That's a high pass filter. So you get only the edges. And again, the results will have positive and negative values. You have to deal with that in displaying. If enhancement is desired, then you have to maintain intensity information, and then you can use a Butterworth high emphasis filter. All it does is it puts a bias, raises the filter, a constant, and if you want to control the maximum value, you put another factor there. If you want the maximum to be 1, then you divide by the max and normalize that. But DC gain is not 0. The rest is the same. So a few examples. The clock image again. Ideal high pass filter will introduce ringing artifacts. Butterworth high pass filter, and this is the Butterworth high emphasis filter. So there is some sharpening here without ringing artifact. That's not good. This is not good for enhancement. Here intensity information is maintained. This area is bright, that area is dark. Here that brightness variation is removed by the high pass filter. This is that myocyte image. This is quite good actually. High frequency emphasis has sharpened some details. The ringing artifact has ruined this. Output of the ideal high pass. Here too, ringing artifact. I should also say there is ringing artifact from the edges because I zero padded. Some of these are non-square images. So for FFT and to apply the Butterworth filter, I couldn't do that with some non-square image. I could possibly do that, but making it a square image helps in the frequency domain. With the Butterworth high emphasis, these details are enhanced. We don't need that. This image doesn't need enhancement. Okay, 4:28. You want to stop here? If I start this, it will take more time. There is just a little bit left in this chapter. We will close this tomorrow and then move on to What is next? Segmentation, is it? Next is segmentation or detection of objects. So tomorrow we will just finish this and move on to the next topic. Any questions before you leave? Any comments? Are you, again, I keep asking, are you following everything and is everything clear? Do you want me to do this in a different way? I don't know what other way, but let me ask that question. Everything is clear? You're able to understand? Okay, thank you. Have a nice time. Maybe you could go to the beach and have some time. See you tomorrow at 9:30.
9:30.
We will start exactly at 9:30. We started at 9:30 and some of you missed a little bit. See you tomorrow. Thank you.